Yeah, so today is Crest Day. I don't know whatever it means. We made that up, by the way. So today is the day when we talk about our research, and thanks a lot for being here and not being outside, where it's really wonderful. But I hope this will be less painful than that, right? So I hope you'll enjoy today. And so I'll do the first bit, 30 minutes, just motivating, setting the scene a little bit. Then Thomas will do his talk and rest of the afternoon. And then after lunch, we'll come back and then we'll do this kind of thing where I set the scene and then people present. Hopefully you get to hear from a lot of other people from the group and you get a sense of what we've been doing. So yeah, I mean, when we wrote the grant proposal, the goal is to make an AI system that learns continually throughout its life. But I think why we really are interested in that, because ultimately we care about making a transparent and trustworthy AI. And I think often people don't make this link. So I thought this is kind of my opportunity to maybe make a pitch of why incremental, continual, distributed, lifelong learning is important. It's because in my opinion, there's no other way to go other than doing incremental information processing if you are really interested in making transparent and trustworthy AI system. It seems like a very long jump, but I hope this next 30 minutes, it'll make a little bit more sense than what it is right now. But before I get into that, let me just give a very brief summary of the project. I think on the first day I told you a little bit about the history of how it came out to be. If you haven't seen that bit, it'll be in the recording and you could see. So we've been actually thinking about this for a long time, is what I was trying to tell people. And the words Bayes and duality, that exist there because we have a lot of evidence that it is necessary, essential, indispensable to make an AI system that learns adaptively, robustly, and continuously like humans. So we actually wrote a grant in 2021-ish, and we received, well, I used to translate this in dollars and say, but now it's kind of not cool anymore. If I say in dollars, it doesn't look that much. So I converted back to Japanese yen. So it's 220 million JPY, if I'm correct in that, adding zeros, and it's kind of hard still for me, but it used to be like something like $2 million, but not anymore. And on the French side, we have Julien, who has received 500,000 from the ANR, which is the French side, and the Japanese side is by Crest, funded by JST, if I remember that correctly. Then we have two co-PI, Kenichi Wanai. Kenichi, are you here? Maybe they're not here. And Rio's on a trip. You heard from him yesterday. So there are two other co-PIs. So Rio takes care of like HPC, high performance computing side, and Kenichi is on the theory side, so he's a mathematician, and Julien is a Bayesian like me. So that's the group, and tell you a little bit about the Bayesian inference group. So we used to call it approximate Bayesian inference, but I really don't like the word inference these days, because I'm not really doing inference, I'm doing more like learning. So Team Approx Bayes is a good description, and so we cannot have PhD students, so we have postdocs and research scientists. We have two and visiting scientists. People are interested in that kind of position. That is quite nice to have. It makes you easier for you to travel here. We also have interns and part-time people who come from university and spend some time with us. So most of these people are here. So I hope you have met them or you will meet them. We have two new postdocs starting and just next month. So I thought I'll put their names here. So Christopher works on interpretability and Johan works on continual learning, and we have another person coming in. So the group kind of is very dynamic, diverse to some extent. Okay, and just wanted to give you a sense of what we have done in last 8 years. So I was the first employee of RIKEN AIP, and I didn't know how things will go at the time, 8 years ago. But this is the list of, I think, 67 people that we have had in last 8 years. And because we cannot have PhD students, the kind of cycle is fast. So lots of people come in, and sometimes they stay like 1 month, 3 months. Sometimes they stay a year. But you know, they no matter how long they stay here, they go on to do interesting things outside. At least one of them is here today. I don't know if you can recognize the name. It's too slow. Alex, Alexander. Yeah, he's here. So he was here with us 4 or 5 years ago. So yeah, there are lots of people. Maybe you have heard their names that have went on to do better things. Okay, so from that I can go to this. The main point of the project is, the main goal is to make AI that can adapt and adapt as quickly as possible. So it has a sense of somehow when things are easy, when things are hard, and then be able to do that repeatedly for a long time. And I like to put this in a very non-technical way. I think it's simpler to say that it needs to make sense of knowledge that is distributed across time and space. And I think that's the simplest description, I think, of this goal. That of course it needs to adapt. At that time it needs to figure out what it knows and what's thrown at it. Is it relevant or irrelevant? Should I really learn it? Should I go for it? And you have to do this decision throughout your life, like a very, very long time. And people actually are extremely good at it, so they do it. So that's why I show this video that I think I quickly threw at you on the first day as well. And if you've seen my talk, you've definitely seen me show this again and again and again, because we're still not there yet, you know. So people can actually randomly explore around the world, and maybe they have no prior information in the beginning, not at least they are aware of, and then over the time they build preferences of these things through observation and start to do interesting things in the world, figure out, so understand to some extent, so that they are able to carry out their day-to-day activity. And then from there on, if things are changing every day, you know, sitting in a room, not having all the information about the world, not knowing who's the president and who is, you know, who's running, what's the concept of country, or they don't know anything. Still, they are learning and generalizing about things that somehow they have observed in that, sitting in that very non-IID non-stationary setting. So that's something that we cannot do right now with machine learning, right? So I bring it down to a very, so this is not a machine learning system, of course, but it's an analogy to show the crux of the problem is that we don't know how to adapt, how to make sense of little changes in the world. So we don't know what knowledge is there in our head. And we are, sorry, when I say we, meaning our systems that we design, they don't have notion of what they know and what has changed in the world, so that they should adjust and adapt their knowledge, right? So fixing machine learning is what we want to do, and I think this is really the core of the problem. Something small has changed, and you cannot quickly adapt, and you need to go back and like run things quite a lot. So you can't do this in an you know, in an adaptive online fashion. So that kind of goes back to then why we are doing the way that we are doing things, right? Let's just scale things up. Let's just throw all the data, throw all the compute, and then this only works for certain problems, very specific problems. So let's formulate all problems in that way. So we've gone backward, right? Because we know how to do this, so we formulate all problems in that way. So then that leads to all the pollution that we are creating, like unsustainability, economic cost, of course, but also environmental cost, and all sorts of harmful things that we are seeing, like privacy issues. That's because we have just taken all the data and just thrown at people, and we haven't done our work that we need to do. We need to be careful. Right? So I really think that we need sustainable, transparent, trustworthy AI, and I'm repeating this message from first day, but I think it's worth repeating, and maybe I'll be repeating it for a few more years. Hopefully things will turn out to be better, but I really want to say that the goal of our right now, what we really need is sustainable, transparent, trustworthy system. And you're not going to make it if you continue to do things the way that you do, right? Taking all of the data at once, throwing all the compute scale, at the same time, this is not the way forward. What we need to think about is like how these kind of systems are made in other domains, right? How are bridges made that don't fail? How are medicines made that really work for a huge number of population, right? The key there is some kind of reliability in building blocks that we have, right? So we need to think about what kind of building blocks we have, and in our systems we have data, model, and metrics, and we need to figure out how they are contributing to the behavior of the model. We need to somehow figure out how these things come together and then interact with each other and give rise to this emergent magical behavior that we see in our language models, for example, right? And I think what I'm trying to say is that you cannot do that unless you do things incrementally, meaning that if you want to make sense of what you know and what you don't know, and how what you know impacts the behavior that you see in the model, you need to process information slowly. Just like a little kid. I mean, they're constrained in a little room for a reason, perhaps, and they cannot walk. They have to learn to look, and they recognize faces and eyes first, and somehow evolution has kind of find a way through this, because maybe that's the most relevant information for them that they are figuring out, right? So so we are all doing this. We are slowly seeing knowledge over time as we live, and we make sense of it. We compare our new knowledge to old knowledge, and we either learn something or we forget something, right? And I think building incremental systems is the way to go this. And so I want to I'll present just in next slide, perhaps next slide, mathematical argument for this, and maybe it'll make more sense at the time. So what I think is there is Bayes sitting in there, and for me, Bayes duality is a solution to do this. So thinking about perturbation, sensitivity, duality is one very first principle solution to this. And then Bayes sort of is there whenever you think about that. So that's something that I want to convince you. So today, this whole day is sort of about this, about thinking about, of course, we don't have any results on trustworthy AI yet, but that's what we are thinking about. That's the big picture that we want to solve. We want to build sustainable, transparent, trustworthy AI systems, and we want to somehow come up with some fundamental ways to know reliability of the components that we put in that system, right? And then we want to somehow demonstrate these things on incremental learning. So that's what we will try to convince you repeatedly through many of our works that we have done, that this all actually is connected together. Sorry, this is a difficult sell, but I've chosen to do this. I don't want to just do, huge model and look, this is so amazing and you're impressed and give me money, right? I'm a scientist, so I want to do the work that scientists do. I want to convince you. Okay, so the summary of the results that we will present is this 10 papers. There are a little bit more papers, but I ran out of space, so I didn't write all of them. But we'll first start by thinking about, how Bayes comes in when you start to think about transparency and trustworthiness in a system, and then try to connect this to deep learning, what's happening through Bayesian learning rule. And then I will hand it over to, so that's hopefully next 15 minutes. Then I will hand it over to Thomas, who will talk about SAM, his work on SAM. And then after that, he and his group, his team will talk about training GPT-2 from scratch with Bayes, which is something that we are very happy about. And then in the afternoon after lunch, we'll talk about knowledge transfer. So I used to talk about continual learning a lot, but I realized model merging is actually an easier topic to think about. So I first talk about model merging, and then you kind of start to see some what did they call it? Sparks of duality. Okay, sparks of duality. You may see, and then we'll also extend this to continual learning. And then in the end, we will end with the hardest problem that we have is figuring out what we know. So talk about memory. Okay, and okay, so I have 14 minutes. This is very tough, and I thought I will include questions as well, but we'll see how I do on time. Okay, so let's start with this a thought thought experiment, right? This is what I'm going to talk here is definitely not feasible in practice, but let's think about how to build a transparent, trustworthy AI system, right? So as I said, one way to think about is to think about building blocks that you have, right, made up of. The system is made up of. So in standard deep learning, you're just given a huge model with parameters, right? You don't know what training data has been used or what settings have been used. More or less, it's kind of opaque. And I think that's a problem. But if you really want to know what this system could have been if I use something different, right? So you want to understand why it works the way that it works. Like, what's the value of New York Times data? Like, is it worth getting sued for? Right? Should I be really using Reddit in my language model? And we may have some dangerous behavior, but can I do that? Should I do it? I mean, that kind of question we want to ask in the beginning when we want to build a system that's trustworthy. And one really infeasible way to do this is to train many models, right? So suppose retraining was not an issue, and you could simply remove New York Times data and then retrain the model, and then you could test, you could compare the performance between the two models and see how they differ. And that would actually help you to understand how New York Times data has affected the decision of GPT. You could do it for all possible subsets of the data, suppose, and you can build infinitely many models. Then you could always go back to, if some issue arises that my model is calling black people something, right? Then you can go back and you can actually undo your mistakes because you have kind of thought about it before. It's there somewhere. So that's one, I mean, it is infeasible to do, of course, but it's also telling you the complexity of the problem, right? So you could do this, and you would think about it as like, oh, I'm perturbing the data. So you would say, why is it Bayesian? There's nothing Bayesian about it, and Bayesian people are doing something else. This is a frequentist world, but I can tell you very precisely that actually thinking about all possible exhaustive cross-validation leave-outs, actually it's equivalent to the partition function of a Bayesian problem. Okay, so there's this paper by Möllenhoff, it's quite beautiful paper, which tells you, which shows just in a few lines that marginal likelihood of a posterior is equivalent to doing all sorts of leave-out, exhaustive leave-out cross-validation error, right? So it's sorry, okay, you don't like this.
Then you have to leave not only the New York Times out, but all possible combinations.
Yes.
So the statement is not what we thought.
Okay. Okay. What did I say?
You said that the way you kind of constructed by having a bunch of data, you take out New York Times and you put it in, this kind of thing is actually equivalent to the marginal likelihood. No. If you take all possible combinations of how you put data in, that's fine. You can think of this kind of cross-validation as like a first-order expansion of the marginal likelihood. Okay, so, but in this wide framework, it's fine.
Yeah, maybe I misled you.
It's related.
Yeah, what I'm trying to say is that I'm not interested in New York Times. That's OpenAI's problem. But I'm just saying, if you want to build in general a transparent system, right? Like a bridge that you build, and you think about how would the bricks that I put in there, or the material that I use, concrete that I use, how does it affect? Then I must think about replacing that concrete by something else. And then I know, and engineers do this all the time. When they're making these things, they have actually done this study that this material will give rise to this much, stability. I don't know how they do that exactly, but yeah. In engineering systems, you can actually do this kind of performance analysis. Does this make sense?
Whatever.
Okay, whatever. That's the right start. So it's been only 20 minutes in, we are whatever. Good. So, okay, we're having conversation, and even if you're not convinced now, maybe someday you will be. But what I'm trying to say is that think about perturbation as thought experiments. And being Bayesian is crazy for the same reason that doing this all exhaustive cross-validation is crazy. Right? So I'm not kind of saying that we should be doing this, but I'm just trying to say that if you start to think about perturbation to understand what contributes to your system, then that's actually related to perturbation through the posterior. Right? These are kind of two different views of seeing the same problem. One may even say it's a dual view, but I'm refraining from saying imprecise statements because people don't like that, right? But I'm just trying to say there's two sides of the coin, and Bayesian thinking comes in naturally because sampling from a posterior and perturbing in the parameter space has a similar effect to thinking about perturbation in the data space, at least on the whole. Like all of these perturbations sums up to be all of these exhaustive cross-validation error. Okay, now the problem is that people actually usually think about Bayes like this, right? When we say with quantifying uncertainty, what we know, we usually think about model parameters, and we say, oh, if I want to know if I'm segmenting my image right, I should sample from my posterior, and I should look into different, well, these are also like somehow perturbed parameters. So these are different models, and then I'm trying to average their predictions and look at how they differ, right? But this is a different way to think about Bayes, but that's an alternate way to not think about perturbation of the parameter, but think about perturbation of the data. So somehow the effect of this perturbation is similar. Okay, Howard is not smiling, so, but I will continue to do that. Okay, all right. So suppose that you agreed with that view, and if not, please read the paper and make up your own mind. But I haven't proven anything about duality there, right? But what I'm trying to say is that if there was a way that I could actually create many models, many copies of my model that somehow differed in smaller or bigger extent, so maybe data sets or some other training condition, in a way I would actually have a method to tell what the system is doing and why it's doing that and how I can fix it, right? Because I could take out some troubling parts from it. But it's impossible to do because in deep learning, as you know, you have only like one weight vector, so it's very convenient. But if you start to go this retraining way, then you have to store weight vectors for every model that you do, which is of course impossible to do. And so if we have some way to somehow approximate this, then that would be quite nice. So in the approximate Bayes world, we do roughly kind of this kind of thing. So what we've been thinking about for some time is let's do the simplest possible approximation that we could think of, right? So add a variance vector, and now I try to perturb each weight element of that weight vector separately, and that may give me some idea of some different models generated in that way. So they're all kind of independent of each other. Of course, that seems like a silly thing to do, but we are saying let's add just one variance vector and see what we get. Our system's becoming slightly better. Do we have a little bit more idea of what the model is doing? So this is what we've been actually working on for all these years. So say, let's just add another estimate of a variance vector and see what it brings to us. Okay. So Thomas will actually talk about a method that that estimates this weight variance vector using something like Atom. But I've been actually thinking about this for a while, and this is the paper that it was in making for many years, but it's published last year. But there we show that actually this simple approximation that you do, so just think of just Gaussian, where you have a weight vector, which is the mean, and then a variance vector. That Gaussian seems to be actually, if you actually use that posterior approximation, then you can show that these very well-known algorithms, they are somehow estimating this this kind of Gaussian, very simple Gaussian. So sorry, maybe I didn't say it in the best way, but basically we have a new learning rule, which is we call Bayesian learning rule, and we can show that these algorithms, they can all be obtained as special cases from this Bayesian learning rule by choosing a very simple posterior distribution, something like Gaussian with fixed covariance or sometimes covariance, a mixture of Gaussian. So they're all sort of Gaussian based. So this hints us that perhaps adding a variance vector, just one variance vector, is not that crazy an idea. And maybe it helps us to connect to this deep learning world where where things are completely non-Bayesian. So then what we've been working on is to somehow take these algorithms, see them from a Bayesian viewpoint with these approximations, and then try to relax these approximations and see if we get some improvement. That's kind of what we've been doing for a while. And so Thomas will talk about SAM in that light. Anybody has any questions?
Just a quick question. Ivan is not here. If you can figure it out.
Yeah, Thomas will spend like an hour on that. So yeah, in half an hour, hopefully. Okay, sorry. Any other question anybody has? Okay, so I'm running out of time, but I have to do a little bit more. So, okay, so so I just wanted to give you a little bit more. So I did a tutorial on this, but that was another kind of disaster. But let's try to, So I think many people ask me like, oh, I have this thing that is Bayesian, but then so what, But this is why what, right? So what we get out of that is that now this Bayesian learning rule can be somehow seen as a unified framework to derive algorithms or improve them. So it's just a different viewpoint, and we are trying to then use this as a guiding principle to improve things. That's what we're doing. So just going through very quickly over this construction, how it works. You start with an exponential family, so like Gaussian, where you have natural parameters. Let's say lambda is a natural parameter in a Gaussian case. So it's in Gaussian case, you basically have quadratic and you linearize it with respect to quadratic, which is a weird thing to do, but quite amazing actually when you get to know this procedure. So you're somehow assuming that quadratic is a linear in some other lifted space, if you like that word. And then this coefficient is, this is precision times the mean. You can also think of it as like somehow Hessian times the mean. You will see this again and again throughout this day, so I just want you to remember this, that somehow things are linear with respect to this quadratic sufficient statistics, and one of the parameter is not mean, it's the precision times the mean. So somehow things are additive in this space is what we will see, and we'll see this repeatedly throughout the talk, okay? Throughout the day, sorry. So essentially, so yeah, you have this natural parameter, which is this precision times the mean, and then you have precision as another natural parameter. We'll usually talk about this, so just remember that. But there is an alternate dual parameterization, which we call expectation parameter, which are like mean and the correlation. And then Bayesian learning rule is somehow using this duality to do a natural gradient descent in the lambda space by computing gradients, natural gradients, with respect to mu. So if you compute the gradient with respect to mu, it's a natural gradient, it's computed in the dual space, and then you bring it, take the steps in the lambda space. Okay, so why this was a good idea is because this natural parameter space is a very natural space to talk about information addition. This is something that I talked about in the tutorial. I said you can think of multiplication of distributions as addition of natural parameter. Somehow you're adding information in the natural parameter space. And this is another thing that you'll see repeatedly, that we make use of this principle that things are somehow additive in this space. The simplest example that you can think of it by thinking about Bayes' rule, which is a multiplication of the likelihood and prior. But you may actually kind of see that if I take log of it somehow, then it should be an addition. So of course, I have ignored the constants here, but somehow going in the log space turns this multiplication into addition. So then it looks more similar to doing gradient descent, where you have addition of gradients. So that's where we are going. And so the exponential family is the simplest way to kind of write this. So you start with the exponential family for the likelihood and for the prior, and if you multiply them together, then you can equivalently write computation of the posterior as just addition of the natural parameter for the likelihood and the prior. So it's a little bit non-standard, but I think this is kind of the way that I try to connect these Bayesian computations, which I call conjugate computation in this paper, to somehow connect it to gradient descent type of algorithms that people use in machine learning. Right, so I don't have time today to go over this, but on the tutorial day, I actually showed that this computation can just be written through gradients. So somehow combining these two forms, so like you are updating the natural parameter, but you're taking the gradient of this top guy with respect to mu, and because these both are linear in t theta, the expectation is linear in mu, and then you just take the gradient of this to get this. So this is just what I'm saying in the end is that this is a different way to rewrite Bayes' rule, right? Where you simply do an addition and update the natural parameter. Okay, and from here we try to extend this. So this works in the exponential family case, but if things are not exponential family, then we can still use the similar procedure by using posterior approximation instead of having exact posterior, and then taking these gradients. So that's kind of roughly how it goes. And to do this extension beyond exponential family, essentially we have to resort to the optimization formulation of the Bayes rule, which I also talked about the other day, so hopefully I don't repeat it today. But essentially you can rewrite this KL with entropy, put the prior somehow inside this loss. If you don't have a prior, that's fine as well. And then you can basically apply that rule onto this objective. So this is how you connect the world of the non-Bayesian world and the Bayesian world, that you, instead of doing gradient descent on this, you do natural gradient descent on this. And if you write down the natural gradient descent to update the natural parameter, you get that. Sorry, this is very, very quick, but I can stop and, but you should read the paper or attend the tutorial, or just talk to me. So we have time, but yeah, this is not something that you can just learn by looking at it once, unfortunately. And that's why I think our work has slower impact. It takes time for people to understand. But if you have to take, one or two things out of this, just think of it like you're updating, you're somehow adding natural parameters and natural gradients together. And this addition makes sense because of a Bayesian reason, because they are kind of all natural parameters. So natural gradients are sort of natural parameters. Sorry, I'll give a more faster, anyway, I'll skip all this because I did all of this, but so this is the table that I showed you. So if you didn't follow any of this, just go back to the table. So there were different posterior approximation, and then there were different natural gradient, and then you do these two things, and with that you can get different algorithms. So essentially that's kind of what I wanted to say. Okay, I'll skip the example, and okay, so this will be my last slide. And I'll end with this, and I'll give it to Thomas. And then we can. So this is just setting the scene. Not even if not everything makes sense to you, just remember the Bayesian learning rule, and let me also tell you very quickly what is the dual view of Bayesian learning rule. And then we have whole day to understand this. okay? So that we're going to do it like that. So the dual view actually arises when we start to think about what our system is made up of. Okay, so let's think about the simplest component of our system, data, right? And the loss functions, they are somehow additive in data. So you add all of these loss functions over the data. And if you actually apply to the Bayesian learning rule, so you say natural parameter is somehow updated using the sum. So the sum was not there in the previous one. And you're now adding all of these things up, right? If you think about what this iteration actually does, you can think about, you can average over the whole history. Like you can see lambda as somehow made up of all natural gradients. I mean, if you think a little bit more, you would convince yourself that lambda is somehow lies in the space of the natural gradients. It lies in the space of these delta mu, nabla mu, okay? It's another way to write it is this, right? So I'm saying that I could just kind of rewrite it because it's kind of moving average. I could rewrite this in this form where my lambda is made up of all of the natural gradients over the data. So this is what I call the dual view, and for reasons that may not be clear right now, but we don't have to get into that to use it. What I'm saying is that there is a lambda, the natural parameter, is made up of all of the natural gradients over individual examples. So somehow I have a relationship between how each data contributes to this global parameter. And each data is somehow a local parameter, okay? And you can simply add, so I'm gonna denote this by lambda tilde, and in the tutorial I actually started from here and try to go to Bayesian learning rule from here. So you see why I was doing all this. But because this is kind of how, the Bayes rule is set up, is that there are lots of these components, and then when you multiply them together, they give rise to the posterior. In log space, it's simply natural gradient. So I cannot stress enough the importance of natural gradient, and I will die on this hill and I'll fight with you. But really, this is not site parameter, right? This is natural gradient, okay? And it arises because it optimizes the Zellner's formulation, the Bayes rule, the optimization, variational objective, all sorts of things you can call. But you add natural gradients and you get natural parameters. Okay? This is the key point, and this is the equation. On first day I said, oh, we got all this money because of this equation. That's the equation, okay? And everything that we do is based on that. So everything, really, almost everything that matters. So, okay, why this is important, and I'll finish with this. So I haven't proven that this is a theorem, but it is a representative theorem, that it represents the lambdas using these lambda tildes. And you will, there will be a paper written someday, but I've done these calculations. You can actually derive the representative theorem that you know from this. Okay? And it doesn't seem obvious. It is not. Okay? But it is kind of so I believe that it's a more universal representative theorem in that sense, where we see that natural parameters, they arise by simply adding these natural gradients. So the important thing is that the larger natural gradients contribute more. So if you want to know what data examples are really contributing or important, like was it Reddit, or was it New York Times, or was it something else, then you could actually start to think about these lambda tilde i's that corresponds to those data examples, okay? And they're additive. So that says something, that if you remove them, somehow lambda is gonna move a lot, okay? And that's kind of the point to start thinking about how to build a trustworthy AI system is through this equation and this viewpoint. So, yeah, in very simple terms, the first thing that I'm saying is that knowledge can be represented by natural gradients. And this is this is the hypothesis that we are putting forward. And I'm suggesting that this can be then used to understand the usefulness of a component. The second thing that I'm saying is that knowledge can be transferred by adding and subtracting these natural gradients. Okay, so now I want to use this for incremental continual lifelong learning. So this is the plan, and we have 3 more years to go in this project, maybe slightly more, but this is what we want to do. We believe that this equation, this is kind of what we call Bayes-Duality, because the Bayesian view, the Bayesian solution has a dual view that, in my belief, encompasses all the other things that we know in machine learning, and perhaps is related to many things, many dual views that we know in convex optimization and in information geometry. So I think it's theoretically a sound principle to go on. I haven't shown this yet, but I'm just one guy. Just wait for 10 more years. But first I want to see if it works. So we are applying it to knowledge representation, to knowledge transfer, and we really want to show that this duality will be useful. So today there will be some examples of this that you will see, and I hope that we can go back to this slide and keep thinking about it if this is actually making sense. So I'm completely fine if you criticize me, and if you say that this is all bullshit. I said bullshit on this. Okay, so, which is fine, but this is why we are here, and this is Crest Day, so it's not just to celebrate and you to say, oh, you're so amazing, everything's great. No, we want to talk and we want to see how much of it makes sense, if it's useful for you, if it's not, we want to discuss and talk, okay? So Howard has already started the trend, so let's keep that up. So with that, I finish my talk.
You started your talk with the pictures of your children playing, which is really cool because you're showing physical knowledge, like how to interact with the world, how to achieve goals, and then you have this. So you're saying that this is, you can represent all the knowledge you want with this. There's several steps in between there. Can you help me connect those dots?
Yeah, I think it's, yeah, thank you. I went very fast on this and I apologize, but there are more interesting things coming after my talk. So yeah, I think the way that we do this is that we know that this update is related to all of those other machine learning updates like gradient descent, SGD. So we want to then, and here we have a very nice additive form. So we think that this helps us to understand kind of stability and sensitivity of those algorithms. That's kind of does that make sense? Maybe too many. Yeah.
Maybe just, so you say we can do all these learning rules this way, and because machine learning can give us a representation for knowledge, therefore we have it. But one might argue that we're still not sure how we should represent knowledge in machine learning if we want to build a PGI system.
Exactly, yeah. So I don't know, but what I see from this, so if you see gradient descent as a special case of this, then it suggests that gradients are somehow new knowledge. But that is very limited, we know, right? But then we say, oh, let's now think about Newton's method or Adam, and then it gives you slightly more. It goes into this S times M. So gradient descent is only about M, which is the mean, and the Adam kind of thing, or Newton's method, is about S times M, so it's like Hessian times the mean. And we say, does Hessian times mean represent more knowledge than mean? And this is what we'll show you today, and it does. It does better things. So then it's pointing again to this thing that we cannot do, is that we should have more flexible posterior. So is there another way to do this? And I believe that you can actually do it. Yeah. Makes sense.
Sorry, I had one quick question as well. So if I'm looking at the terms that you have there, right, they depend on the parameters themselves. So like if I see New York Times early in training or later in training, they would have a completely different effect on the training. So exactly. How does that play with this sort of additivity? Because it's not additive anymore if it depends on when you compute it.
Yes. So great point. So you're exactly right. So I think things are additive only locally. Right? So in the near time, things are additive, but then in longer ranges, things are not additive. But I think you can actually, what would you do if you have a curve that's kind of crazy? You would try to go and find places where it's straight and you'll draw a line, and where it changes a lot, you have to draw more lines. So that's kind of what we call memory, you will see. Okay.
So, I think your talk title at your beginning was talking a lot about transparency and trustworthiness.
And this was more about, I guess, like optimizers and incremental updates. Can you comment, like where, like how, like any of these optimizers in the table, like why exactly they give you more transparency?
Oh yeah, thank you. So okay, so I have a very fundamental bias, you may call, but strong belief that I think talking about post hoc things is bad, in my opinion, because once you have done the crime, you cannot go back and undo it. So when you're actually committing crime, like stealing New York Times data, you need to think about it at that time. So I think we need to think about iterations of the algorithm, not the solutions. So all of this stuff is actually made so to analyze algorithms. When you're running the algorithm, I want to use the dual view to understand what that iteration knows, right? So if the iteration is really flat, then I know that things are more or less linear, so they are easy to represent. But if lots of crazy things happen, then I need to kind of store more things about that. So like I need to think about, like when I'm adding useful information, I need to use this equation to understand how that parameter that I got at that iteration come out to be. Does that make sense?
Yeah, I kind of had a specific question. Maybe you can just ask about what Thomas can answer it later because I
Yes.
forget it. But like I was wondering, like, does this optimizer, like in GPT-2 training from scratch, like help you in all these like hallucination, like these weird kind of problems? Like, so maybe we'll first hear about that.
Yeah, we haven't gone that far. Paper just came out this year, but he has some result on sensitivity on ImageNet, which looks quite good. Yeah.
So you said that this whole outside exponential family with approximate posteriors, that really wasn't clear to me because, for example, the existence of mu is kind of reliant on being an exponential family. So I kind of see how all of this adds up in the exponential family. I don't really see how any of it adds up outside of that.
Yeah, that's a great question. I also don't know. So that's why we have mathematicians here who I think Koichi is sitting right here, and he has a poster where he's sitting right here. And he has a poster on like how to extend this to like Lie groups or like other kind of beyond exponential family. So I also have a strong belief that this is a more fundamental principle, but the mathematics turns out to be much nicer in this case. So you're right, I don't know what happens, but right now just doing Gaussian and make sure Gaussian is still okay. So yeah, we can, and T distribution kind of thing we can still handle. Yeah. Oh my God. Okay, this is not gonna be good.
No, it's fine. I just want to comment on your question because it's like you said that the kind of knowledge depend on, in order to kind of bring in the data, but this equation is quite clear. It's like all the data need to be present at the same time, and this kind of property is valid at the mode, at the optimum. Yes. So if you bring in data another thing, you're kind of changing this thing. That's not a problem. And then things change a bit.
Yeah.
If you're having data sequentially, this is another thing. But here is like the imputation is at mode.
Can I comment?
I see what you mean, but like even if you do full batch, so there's no non-stationarity, you just compute everything at once, you still need to do multiple updates, and all of those updates are going to be quite different because of nonlinearity of the function. Basically what's happening is that we're linearized a lot here, and potentially the neural network can be quite nonlinear, so therefore this cannot really express what the neural network does. That was kind of my argument.
Yeah, I think I would agree with that. Well, maybe we could talk about this after because I think we are stealing time from Thomas. So maybe we should stop now. And we have 10 minutes now, so.
Okay, so I will give a quick 10-minute talk on this, and then maybe if someone has questions, they just come to me in the coffee break and we can discuss. So MT talked a lot about connecting Bayes to popular deep learning methods. And in particular, there has been a very successful deep learning method called Sharpness-Aware minimization. And in our work, we connected that to Bayesian principles. And maybe to give you a quick overview, this is the paper. One of the authors, Hossein Mobahi, he's actually in the audience here, I think. And the paper has already been cited over 1,000 times, so it has been extremely successful in deep learning, and it can, for example, improve test accuracies for residual networks, transformers, language models. But it not only improves the accuracy, but many other aspects of deep learning that MT also talked about, which are desirable, like robustness, calibration, interpretability, transfer learning, compressibility. It works on federated learning, and I think I made this slide like already a year ago, and now there are probably many more papers coming out on showing how this works. And so in our paper, we show actually that the objective that is proposed in the SAM paper is equivalent to a relaxation of the classical Bayesian objective that MT has in his slides. And this relaxation is obtained using a convex duality. So it's some kind of convex approximation. And based on this, we can also propose new algorithms that can add uncertainty on top on SAM. So the Bayesian interpretation of SAM helps us to get uncertainty estimates for free out of SAM. And yeah, we hope that this works can open a new way of kind of viewing deep learning methods from a Bayesian viewpoint and using that viewpoint of improving them. So very quick, what is SAM doing? So we are here in our parameter space. Theta are the weights of our neural network. And instead of minimizing L of theta, which is just our sum of the individual loss functions, we are minimizing L of theta plus epsilon, where epsilon is a perturbation that's taken within a ball of radius rho around of our parameter. So in some sense, we're looking at some kind of worst case perturbation of our loss function, and then we want to minimize the worst possible perturbation. What the Bayesian objective is doing, here we consider an isotropic Gaussian posterior approximation. And if you then minimize the objective shown in the previous talk, you end up not with a worst case perturbation, but you average actually over multiple perturbations. And yeah, these two principles, looking at the worst case or looking at the average case, at first glance they look different, but you can see there are some similarities. For example, we have this radius rho, which determines the neighborhood in which we look for the worst case. And in the Bayesian objective, we have our posterior covariance sigma square. So both have a certain sense of non-locality. So we're not looking only at a single point, but we are saying maybe we should care also how the loss looks around our parameter theta. And yeah, what we've shown in our work, which was at ICLEAR last year, that there's a connection between these two objective functions, a very precise mathematical connection, which is obtained using a tool called the Fentel biconjugate function. And yeah, what we plot here is in gray our loss function L. In blue, it's this expected loss that I've shown on the previous slide. And because you're kind of averaging over the neighborhood, what you get is a smoothing of your loss function. So you're smoothing out these sharp minima and non-convexities as you increase your posterior covariance. And then what we prove in the paper, there's a loss function which is under some conditions equivalent to the SAM loss function, and it's always an upper bound to that blue loss function that you get through the Bayesian smoothing. So this is just the graphical illustration of the math. As we increase our neighborhood size, we are smoothing out these minima. Yeah, so we've seen this. So this is like just a technical tool to compute these lower bounds. Maybe I don't have the time to really go into the math, so I have 3 minutes left. But essentially, you can compute the convex hull of a loss function to get a lower bound. And we do that to the expected loss in a very specific parameterization of expectation parameters. So this is the construction. On the left is our non-convex loss function L. And we look at it in this expectation parameter space where omega is the mean and v is the variance of that Gaussian distribution. And then on the boundary here, this is just corresponds to Gaussians with zero variance, and then the expected loss would correspond just to the loss function. So that black curve here corresponds to the negative loss, because in the end we want upper bounds on the negative elbow to get lower bounds, so we do that to the negative loss. And then this blue mesh is just the expected loss, and the red surface is the optimal convex lower bound obtained via the biconjugate. So somehow the construction, how it looks graphically, and then the animation on the previous slide. I was just showing slices through the surface. So the blue mesh and the red mesh, they correspond to these blue and red curves in that animation. So this is just a one-dimensional slice through that surface, but the convexification is done in this very specific parameterization, and this is not arbitrary. This is essential to the construction here. Okay, so yeah, maybe this is the last technical slide that I'll go over. On the left-hand side, we have the elbow. We've seen in Emtiyaz's presentation. We can just rewrite the expected loss using this f of mu notation. This is in the mu coordinate system of expectation parameters. And we have minus f of mu because we looked at the expected negative loss, because we want in the end to obtain an upper bound on the negative elbow. So what we do is we simply replace the expected loss with the biconjugate that you've seen on the last slide. So we get an upper bound, and it turns out this is a difference of convex functions, because the biconjugate is always convex, so minus the biconjugate is concave, and KL for exponential families is convex, so it's a difference of convex problem, and for such difference of convex problems there's always a dual problem, where you basically switch the order of minimization, and then you plug in and do the math. So I don't have time to explain these details, but if you simply plug in a Gaussian distribution with mean m and covariance sigma square into that loss function here, and you just rewrite it, do the calculations, you end up with the SAM objective. So it's not exactly the SAM objective here, I put them next to each other. In SAM we have a hard constraint on the perturbation epsilon. If you do the relaxation of this Bayesian problem, you get a soft constraint on the perturbation epsilon, but you can imagine that they coincide under certain conditions. And also it pops here out in the math that the posterior covariance sigma square can play a similar role as the perturbation radius in SAM, as it penalizes epsilon. And under some conditions, the critical points of these two objectives can match. Okay, so yeah, so this is a nice theoretical connection, but what do we gain from this? We can, for example, now optimize the relaxed elbow using the Bayesian learning rule. So we optimize the biconjugate rather than the expected loss. And using a lot of approximations, because the biconjugate is hard to compute, we can arrive at a practical algorithm that estimates uncertainty on top of SAM. So on the left it's SAM, on the right is kind of running Bayesian learning rule on this relaxed objective. And just running them on a simple toy example, you can see that you not only get a single solution, but you can estimate many solutions by sampling from that uncertainty that the Bayesian interpretation gives you. So we get for free these multiple models. Also for neural networks, this can sometimes improve the accuracy. So if you look at this table on the top, it's just standard SGD training. Here on CIFAR 10 and CIFAR 100. And if you train with SAM, the accuracy goes up quite a bit. That's why people like SAM. But also the other quantities that the Bayesian people maybe care about, like expected calibration error or negative log likelihood, SAM also improves them. And then if you use this Bayesian interpretation and do additional model averaging on top, so I think this is with multiple average models, you can further improve these calibration error and negative likelihood and so on. So to summarize my talk, these successful deep learning methods, SAM, it appears similar to the Bayesian approach, but there's a key difference of using worst case perturbation instead of average case perturbations. We created a bridge between the two methods using Fenton biconjugates. This allowed us to derive our Bayesian SAM method, and it can sometimes give better uncertainty estimates and improve the test accuracy. So that's it, and thank you very much.
Should we still do 1 or 2 questions? I think we should.
Very interesting. Just one question. So, in the Bayesian SAM, you're computing the expected loss under this Gaussian perturbation, ideally. But in practice, when you want to build this algorithm, I suppose you show that you're sampling.
Yes.
And my question is, like in deep models, you have billions of parameters, and my concern is that by just sampling, I don't know how many samples you need to take, but by drawing samples in like that are like within practical range, you may still get very high variance of this estimate.
Yep, very good point.
How does that work? I mean, when you run this algorithm twice, you always see the same result, and this is improving.
So very good questions. So we will report it here the standard deviations. So for sure, there's we not always get the same result if we run it twice. These numbers, this is the standard deviation of the accuracy. Regarding the point for the sampling here, so this algorithm actually it tries to optimize this objective. So it tries to optimize a really deterministic objective. And then, of course, your question is, why do we sample here? And this is more like an optimization trick to kind of get the improved optimization of this function. So this was derived on very low dimensional examples where we know what the solution is. And then if we wouldn't introduce that noise, we were unable to, even on a very low dimensional example, properly optimize this objective. So we're really somehow trying to optimize a deterministic objective here, but introduce that noise. Of course, that noise induces some kind of additional variance, but we didn't find it to be too bad.
I mean, for Bayes, sampling is a feature. It's not a burden. We want to do it. We don't want to get same answer.
I also had a question. So in your Bayesian SAM, you move from worst case scenario to an average case scenario. Can you say a few words why that's a good idea? In my mind, like the worst case scenario was a feature.
Okay, so we are still doing worst case here. Sorry, I think this was confusing in the talk, maybe.
Okay.
So we are still optimizing the worst case here, but we are also learning sigma square. So rho is here set as a hyperparameter, but this Bayesian SAM algorithm is actually optimizing that objective in m and sigma. And you have some regularization on sigma. So it's still worst case. We continue with our recent work on training large models, or maybe nowadays this is a small model, but training language models using variational inference. And the talk will be split in half between me and Yuesong Shen, who's the first author of the paper. So we will switch after 20 or 30 minutes. Share, yes. So yeah, this is the paper that I will speak about. It recently got accepted at ICML, and Yuesong and I we will share the talk. And I think Nico, he's not here today, but he will join later for the workshop, maybe next week. We have Nihonbashi and Clément, they are sitting there helping out with you can stand up also and wave or something, or I guess people see you. So they did a lot together with Rio, who gave the talk yesterday. They did a lot of the large-scale experiments for this paper. And then, of course, MT is also in the project. And he's around, of course. So yeah, please feel free to talk to any of these people. Probably Nihonbashi and Clément, they know the most details, and Nico also, they know the most details what really went into it to make it work on these large models. So of course we know, we've seen it also in the previous talk. Deep learning is quite incredible, and we've seen many advances, but there's challenges with deep learning. And in our research, we try to address like there's two main challenges that we try to address. One of them is adaptation of large networks. So if you train your neural network, sometimes it's difficult to change it. So one is a bit helpless. It's trained on a lot of data, and then how can we really make sure we remove some data? And this is an issue, and there's like machine unlearning challenges to really make progress in this, because it's a non-trivial problem. It's a non-convex thing which ended up in some local minimum. How can we really make sure to remove it, remove the data? And it's a very hard problem, but we hope, of course, we don't claim doing variational inference will completely solve this, but I hope to convince you that this can make at least a little bit of progress, or it can at least be a little bit useful for this adaptation. And yet, because it's hard to adapt these large deep networks, we run into all these problems that I've highlighted here. I mean, people just shut down the models because they cannot adapt them, and when they try to adapt them, they lose important capabilities. So here this Stanford scientists find that ChatGPT is getting stupider. It's important to know whether updates to the model actually hurts its capabilities, so on. And hopefully you will see some examples also in this afternoon, which may convince you that kind of having a Bayesian approach to deep learning can actually partially address this issue. The second big issue that we focus on is understanding. So if we train the model, then they sometimes make very overconfident but wrong decisions, and make up a lot of things. So it's hard to really understand these models. So you know these examples. And model behavior can be unpredictable, and we're looking into fixing it. So these are the two motivations. So we've trained GPT-2 now with variational inference. Then so what? Why? What's the benefit? Why should we care about this? And our motivation is that these Gaussian weight posterior that we get, that it can be somehow useful for adaptation. So if we train with variational learning, maybe the model will be more flexible, more moldable, more easier to remove data, so it gives you some tools, a bit of extra. So we don't do much more than what people currently do in deep learning, but we hope it helps a little bit to just make things a little bit easier. And of course, variational learning is an old idea, and there are many potential benefits that could potentially materialize. So we haven't maybe seen them fully emerge, but I'm quite motivated by these many benefits. So, for example, if you minimize the objective that MT had on his slides, you're explicitly minimizing the description length of your model, of your data. So you try to describe your data using as few bits as possible, and I think this is just the right objective to minimize. And there's benefits in sparsity pruning, quantization. We've seen in last week's talks also. The other side of the coin of this compression is that there's a bias towards flatter minima, and these have been shown to correlate with generalization. So if you use variational learning methods, the generalization should be much better because you're going to flatter minima. It should be useful for continual learning, because maybe more plasticity in the neural network is preserved, and maybe fine-tuning will be easier. So this goes a bit to this model adaptation point. And maybe the last point is mostly what the community is focused on, this uncertainty estimation and calibration. But this is actually the least exciting for me, that maybe if we train the large GPT-2, we maybe don't care so much about the uncertainties. But these other points I find them much more exciting. And these are the main reasons which motivated us to do this work. And maybe the full benefits didn't materialize yet, but we hope to convince you that at least there are some. And maybe as a further motivation, if you're not too familiar with variational inference, so what is it doing? Let's say you just train your neural network. Theta are your neural network parameters. You minimize your loss function and maybe a weight decay regularizer, and you end up with a solution like this. And then, of course, the question is this now a good model or not? And then maybe you train again, you change your random seed, and you get a different solution. And should I use now this one, or was the old one better? And you do this many times, and it's unclear. So very naturally you're led maybe to consider multiple solutions because the data is an incomplete representation of your world. You only have finite data, and then there's some inherent uncertainty in what should be your classification boundary.
But here you have to find uncertainty as optimization uncertainty.
Yes, the model is over-parameterized.
No, but if you run it several times, you get different answer, and this is what you define as uncertainty.
Yes, here this is what I define as uncertainty. Yes. It's not Bayesian uncertainty. No probability.
It's a different type of.
Yes. There's no model, Bayesian model or anything. But so you should be convinced, even if you are very much into deep learning, that okay, you run your thing multiple times and you get multiple answers, and it's unclear which one you should pick. Then you should be very uneasy, right? This should not be, okay, I just go with one and, maybe. So you could, instead of just picking a particular one, you could try to find multiple ones and collect them in a probability distribution, which I call here Q of theta. So this is visualized here, all these individual lines. You ran the optimization, you went to the minimum, you get one of these lines. But instead of doing multiple runs, you could try to collect them in a probability distribution here, Q of theta. We hope that having this Q of theta can be useful because you can argue about multiple situations. And so how do we do this in practice? So let's say you want to find multiple solutions at once. Instead of minimizing theta, you can minimize over a distribution Q of theta. And you minimize the sum of two terms. One is the expected loss, one is the entropy. We've seen this many times in this workshop, but maybe I'll repeat it. So we're searching for a distribution Q of theta, and it collects multiple hypotheses in that distribution. And the expected loss tells us if we draw models from this Q of theta, then they should have low loss. So that's the responsibility of the first term here. Responsibility of the second term is that the solutions drawn from Q of theta should be diverse. So if I would just minimize the first one, maybe I would collapse to a single one, but it's good to keep some diversity in. And what we want to argue here is that if you have now this Q of theta available, maybe it can be valuable for both model understanding and adaptation. And yeah, I didn't mention the word Bayes here, so I just motivated this from a very direct argument that maybe if your model is over-parameterized and there's multiple solutions and the data is incomplete, then maybe you should minimize an objective like this. And so I really like this objective, but it turns out that this is actually connected to Bayesian inference, and yeah, we've seen this many times, so I will skip over this a bit, but you can rewrite this objective, split up the regularizer and combine it here into a KL, and if you pick up prior as e to the minus of the regularizer, and you know that if you minimize this objective in the space of all distributions, your solution has this form. And then if your loss is a negative log likelihood, the optimal solution is the Bayesian posterior. And this is remarked, for example, in this paper here, optimal information processing in Bayes theory. So yeah, this is a kind of a motivation of why we want to find this distribution here. And here it's just visualized in a very simple two-dimensional loss surface. This comes like from a logistic regression problem, that if you just find the minimum, so this is a convex problem, if you go to the minimum of the loss, you will end up here. But if you solve that optimization problem over Q of theta, you will actually end up with a solution here which tries to go to a more flat place in the loss landscape. So it prefers the flatter area. And yeah, it's called I1 here. This is the name of our optimizer, but it's essentially solving this optimization problem that I showed before. So yeah, this is a very simple toy illustration, and of course this is a really old idea. So it has been around, this variational learning for neural networks, at least since 1993. There's a paper by Geoffrey Hinton and Van Kamp on keeping neural networks simple by minimizing the description length of the weights, which is exactly that objective. It's motivated from a compression viewpoint, and they argue this should generalize much better because you're really regularizing your neural network. And then Alex Graves, he was, I think, a postdoc with Geoffrey Hinton at that time. He did this practical variational inference for neural networks paper, where he actually already showed very good results in that paper. Like, he trained LSTMs for speech recognition, and it worked much better than SGD. So it has already been successful over 13 years ago, but somehow the community has not been using variational inference. They still use SGD or Adam, despite some earlier successful works. And then there was another work at ICML here, and also from our group, this was the first paper which trained ImageNet with variational inference. Gave also quite good results. And it has been around for a long time, but somehow the community is not really convinced about these variational learning ideas. And with this work here, we try to remind people that, okay, this maybe is not such a bad idea. And yeah, in the last talk, we've seen that this variational learning for neural networks, it also connects to Sharpness-Aware minimization, which is extremely popular right now in deep learning. So yeah, this was the talk before the coffee break, that this variational objective and the SAM objective, they are actually connected. And one could argue, if you really view SAM as a Bayesian method with isotropic posterior, then Bayesian deep learning is already immensely successful. So these ideas kind of led us to this work here, and people also consider like a direct optimization of the variational objective for fixed posterior covariance. So there's papers like anti-correlated noise injection for improved generalization at last ICML, where they show if you inject noise to your parameter, you get better generalization, but no mention of Bayesian learning in this paper. And they say low pass filtering SGD for recovering flat optima in the deep learning optimization landscape. But in the end, again, it's a kind of a isotropic Gaussian posterior, adding noise to your weights to converge to flat minima and so on. So this is actually was already noted long ago, that adding noise during backpropagation training, it can improve the generalization performance. So there's actually already a lot of evidence that variational learning should work quite well, but nobody has really demonstrated it yet for these large models. And this is now what we did in our work here. We used an optimizer called Variational Online Newton. It's essentially the Bayesian learning rule, running the Bayesian learning rule on this objective here for Gaussian posterior with diagonal covariance. And if you write out that update, the updates look quite similar to RMS prop here. So for simplicity, I removed the gradient momentum. So it's RMS prop, not NM. And the only changes you have to make to go from, so the left one, this RMS prop Adam, it minimizes the loss plus the regularizer. And if you want to add the red stuff, so if you want to minimize the expected loss minus the entropy, the changes you have to make are the changes in red on the right hand side. So there's some noise injection. So this, yeah, so you compute your gradient at a perturbed point, which connects to the SAM or anti-correlated noise injection ideas. And there's a small difference in the way the Hessian is estimated, not as the square of the gradient, but through a quantity like this. And we precondition not with the square root, but with h. And then what you get is a kind of a posterior over the weights of your neural network, where every weight connection in your neural network will have a mean and a standard deviation. In this algorithm, it's really properly optimizing that objective here.
Sorry, in the point one, are you sampling new theta all the time, or are you keeping kind of IID normals fixed for the whole run and computing new theta? Are you sampling a random function, or you sample or you're optimizing a overall random, then you keep the function fixed?
It's a stochastic gradient of this guy, so the theta is, every iteration is different. The theta is always sampled new.
Yeah, but the theta is different, but the underlying normals, are they fixed?
No, they are changed. So the underlying normal is given by m and sigma, and m and sigma are updated. So this is really learning the posterior. These other papers that I've shown, they fix the sigma. They don't learn the sigma. So these papers here.
No, it's more. No, it was more that if the underlying normals that you use to kind of sample theta, if you keep them fixed, I think the whole optimization will be way more stable, because then it will be continuous with respect to changes in m and sigma. You don't have these kind of step functions for every time you approximate. Okay, we can.
Yeah. This sounds interesting, but
No.
yeah, let's discuss it afterwards. Yeah, so this is the method, and yeah, so if you don't have this extra term here, this is exactly what's proposed in that paper here, the Bayesian learning rule, and turns out that if you minimize non-convex loss, then, and due to the noise here, this h hat can also be negative, and we don't want a negative h because it's linked to the covariance, and one can motivate here some extra quadratic term. This was work by Wu Lin and Emti, who showed this corresponds to a more accurate Riemannian optimization of that objective. So the natural gradient descent that these methods are based on is kind of a first order approximation of some Riemannian optimization, and this is a second order approximation of the Riemannian optimization, and you get this extra correction term which helps or which ensures that the h stays positive. And yeah, so this is the optimizer that we propose, and it's actually related to recent second order deep learning optimizers that have been also quite successful. So there's from Stanford, there's the optimizer called Sophia, a scalable stochastic second order optimizer for large language model training. And from Berkeley, we have other Hessian, an adaptive second order optimizer for machine learning. And if you look here at the Sophia pseudocode, it's in some sense it's similar to I1, in the sense that we also have some running average of Hessians, and we do some preconditioned gradient descent using the Hessian. The main difference is that other Hessian and Sophia, they artificially have to inject noise to compute the second order information. So this is what they use is called the Hutchinson estimator, where you draw random noise to get the diagonal of the Hessian. But if you consider the variational formulation, one already has noise available from the posterior distribution. So we can compute the Hessian directly using gradients only. So we hope that this I1 formulation, it has some advantages over these Sophia and other Hessian, because the noise comes out more naturally, and we don't have to, for example, compute Hessian vector products, which they do here in this Hutchinson estimator. And of course, they only do maximum likelihood here. They find the minimum of the loss, whereas I1 really computes an approximation to the Bayesian posterior. But nevertheless, these optimizers have been hyped a lot. So one of the authors, he was tweeting, so Adam, a 9-year-old optimizer, is the go-to for training LLMs. And if you use Sophia, it's 2 times faster than Adam. And you can just change one line of code and you can save $1 million. So these have been quite hyped up a lot. So if you like these, then please feel free to try out also our I1 optimizer. Please.
So, just one comment about Sophia.
Yes.
I was going to say, it sounds good, doesn't work.
Okay. So this is very interesting to hear. We haven't tried it that much, but there were people from Facebook having quite good results. I don't know if you've seen these. One guy from Meta, he was really showing very good results with Sophia. Like, he was not an author of the paper, but he was tweeting. I can show you later maybe. It's like he went up to, I think, 70 billion or something with Sophia, and it was quite good.
Are you also, like, in that like the sample on the slide before, you're also going to take like one sample, like here, like first step, like basically each step you're going to take precisely one sample?
So,
like the theta from the normal, like it's just going to be like every update step you're going to take exactly one, like you're going to sample once, right?
You can sample one or you can sample more. So Yuesong will give more details about this, but if you sample more, it will work better.
I just also wanted to confirm that I don't think Sophia is working.
Okay.
That's a second data point. I had a question. I just want to confirm. So in Ivan, are you using the Hessian or the Fisher information matrix? Because Yeah, I thought it was a t-shirt because it comes from a natural gradient derivation.
This is a big confusion. Yeah, it's a natural gradient method, but not the typical natural gradient method, which takes the probability manifold of the neural network outputs, but it's a natural gradient on the space of Gaussian distributions, which is very different. But it's also natural gradient because just the Riemannian gradient on that manifold. It's a very different manifold. So, and what we're using here is the real Hessian, but in an expectation, so it's an average over Hessians. So if you take really here many MC samples, a million or something, then this one is very close to the average of the Hessians in the neighborhood.
Thanks.
But I wanted to give the same one, but two people already said like.
Sophia doesn't work.
So we have done quite a lot of benchmarking with Sophia. Sophia doesn't work all the time. So you have to be careful when you say your method is kind of like Sophia, because then I guess this doesn't generalize.
Okay, I have to pedal back. It's very different.
It is very different because the step size is conditioned by the variance. It's how neuroscientists would respond.
Or maybe you haven't figured out how to make Sophia work. I mean, I think at Meta they got it to work very well. So.
One guy on Twitter.
Or one guy on Twitter.
Well, our understanding so far is that it works well when you have very large models.
Mm-hmm.
And when you have small models or under parameterized settings, it doesn't work. So it does work well in some settings, right? But it's not very clear when.
Okay. Ours works very well for small models. So. So, yeah. This is maybe a very controversial tweet. So, but it's quite fun, so that's why I put it. Anyway, so I think I will hand it over now to Yuesong, who will really talk about the details. If you really want to use this, what kind of things you have to take into account.
So, hello everyone, I'm Yuesong, and I have been really implementing Ivon over and over again for many times, and then there was a name change in the middle also, but in the end we stick with Ivon. So I will be covering the more kind of practical side, especially if you are a deep learning practitioner and then you want to use Ivon, how does it work? So I'll start with the guide on how to choose hyperparameters. Because I mean, to be honest, like sometimes, like yeah, there are some things to be aware of. So I start with kind of like the maybe more familiar Adam-like ones. Okay, so there are four of them. So in Adam, you have learning rate, you have weight decay, and then you have the two momentum, like or the betas, if you see it in PyTorch implementation. So here, actually, Ivon also has something that somehow corresponds to the thing that you are more or less familiar with. For the learning rate, actually, it's kind of different. Ivon actually, probably because of the preconditioning, Ivon actually needs a much higher learning rate than Adam, which is even a bit higher than SGD normally. And then we find that it's actually beneficial to always try to set it as high as possible. I think this is also the case for SGD or Adam, but then it's like more also like the case basically here for Ivon. And for weight decay, actually is kind of similar to SGD and Adam, the weight decay that everyone knows from deep learning. And then for the Bayesian crowd here, I guess you know that basically weight decay is kind of linked to like the prior, basically set a Gaussian prior with zero mean, and then basically this is somehow linked to the prior position of your prior, Gaussian prior. And also in this algorithm, in Ivon, you actually see two momentum terms, which kind of have like a similar form as Adam updates. The first one, the beta 1, is really just like momentum that we just add, so somehow the gradient updates kind of a bit smoother. So this has the same behavior as other algorithms, and everyone set it 0.9, so it works. You can also set it 0.9. For beta 2, actually is somewhat a bit different. Here, actually, you need to set a value that is very close to 1. This would mean that actually your update for H, Hessian, or basically posterior posterior precision is actually kind of have a very high momentum and is upgrading slowly, probably because it's very noisy, the estimation. And then if you don't set it close enough to one, the training can become unstable. And then there is actually, there is actually another view of this beta 2. We write it like this because it somehow makes a connection to the Adam update and then this momentum idea. But actually, for example, if you move this beta 2h to the other side, and then you see that line 5, actually, you see 1 minus beta 2 everywhere. This is because 1 minus beta 2, you can actually kind of interpret it as actually the step size for the H update or for the kind of posterior precision update. And so this is another equivalent view of this beta 2. And there are two more hyperparameters that are kind of like IVON exclusive. So first of all, there is the sample size or the expected sample size. So basically, in the elbow loss, we are optimizing the elbow loss, and in the elbow loss, you have the data part. Basically, you have like the expected log likelihood, and that if you make ID assumption, this is something that would depend on the data size. And you have the other part, which is a K-out with respect to the prior, and there is doesn't depend on data size. So basically, you know that basically the data size will somehow show up somewhere in updates, and then you need to specify it. And here we actually allow the freedom for users to actually choose a different size for the real like training size. But actually in practice, we found out that for many cases, actually you could just set the expected sample size to be the real training sample size, and it works. You don't really need a code posterior or temper posterior to actually make it work. It can be helpful, I think, for like fine tuning. And Nico is not here; he did this, but yeah, there are some cases where it can be helpful to set a different size. And then finally, we also need to determine how to initialize basically the age here. Basically, it's just like the Shen of the log likelihood part, or actually it's the also kind of like an initial posterior precision, and then basically that will somehow affect how we also go sample here. Similar to like the weight updates or in the kind of our Bayesian formulation or the DI formulation, like the initialization of like the mean of the posterior matters, but also initialization of like the precision part also matters. And then here, basically, if you choose this H0 to be too small, meaning that basically the variance, initial variance is too high, then you have too noisy samples, and then the training can become unstable. And the other way around, it can become like too deterministic, and then you end up just doing something similar to SCD. Maybe it's also not what you want. Yeah, and maybe just like one comment here. Here the age is actually rescaled by here. That's somehow, yeah. And then, so age is not directly the Hessian, but it's actually scaled by the sample size. We do this so that somehow the value looks nicer, and then it's kind of independent to the sample size that we are using. It's easier to set it up, I guess. Yes, I already have questions.
Does your setting work with any n or any lambda?
Sorry?
Does your setting of this minimization work with any lambda?
That's kind of the hope. Yes, I think it is. Of course, like if you like typically if you work on one task, basically your sample size is kind of okay. We haven't really tried on continual learning actually. So, but like if you just do like on fixed size, I don't know, do some kind of tasks, actually your sample size is kind of fixed. You only need to just tweak it once, I think, somehow. Or I don't know if that answers your question. So.
I think you want the covariance basic sigma to be basically initialized at some value in basically the same value as, let's say, the covariance being like 0.01 or even smaller. Okay, our experience in terms of working with very precise, you want to initialize the Q values to be very small. Okay, so that means if you typically just fix a init Hessian H0, right? I think this H here, right, that it will depend on your n.
Yes, yes.
So it means that when you have a small n, you actually want to have bigger h, I guess, in definition.
Yes, or you can, you can set the n to be a bit, like lambda to be a bit higher, and then you can set it. You don't have to fix this expected sample size to be the real sample size.
Okay, you actually see
Yes.
some kind of template posterior according to the task.
Yes, but then, yeah.
Okay.
Yeah, but actually in practice, actually we did many trainings, and actually often you don't need the code posterior. You can just do the real thing, like with temperature 1, and it still works. Yeah, maybe like I think maybe in the demo actually we actually used some higher lambda here, but then that was like, I don't know, 150 samples, and we will see later. There's a small demo, yes. But then for typical, I don't know, like sci-fi training and stuff works with temperature 1, yes.
Do you think there is any redundancy between lambda and h, like the posterior precision? Can we somehow cancel lambda, say? It seems lambda is very redundant.
Good question. Yeah, actually, we had many different variants of. We have really implemented many different variants of IBOM, but then here, these two things are not redundant. Basically, they really like encode different things, and then basically, you see that basically like there are parts where only like H appears. For example, like the precondition here, you only see H. But then, of course, when you draw samples, basically at line 8, basically here, the samples, it's kind of, they are together. But then it's not always the case.
I think maybe to me, this is questioning the code posterior work that was understood by some people. So I think we didn't find it. I think people who couldn't make things work, they could say, oh, it doesn't work because of this, but we made it work. We didn't have that problem. And sometimes it does matter, but many times it doesn't.
Yes. So yeah, I just quickly oh, sorry, there's something else. Yeah. So there are some additional tricks, basically. I'll just go through them very quickly. So for transformers, we find out that it's actually helpful to actually do some alias clipping of the preconditioned gradient part, which is kind of like here. I think you also see it. I think it's quite common. I think it has something to do with somehow how transformers are defined, their structure. Like you would also see this, for example, I think in Sophia, maybe you guys still remember there was some clipping there. Of course, like here, actually this pseudocode, we actually write it with only a single sample, and it already works super well using a single sample during training. And basically all the experimental results we're going to see are based on single sample. But of course, we are drawing sample to estimate the expectations in the elbow loss, and then there's no reason why you can't use more if you have the compute. And then it would get a bit better result if you use more samples. And and then you can also actually accumulate and I think it's also used in transformer training. You can also accumulate over different, like several millibatch samples to somehow have like a kind of like a larger effective millibatch size. I mean, it also works. You just accumulate the gradient and then the estimated Hessian over multiple steps, and then you just do the average over them. Maybe there are some other tricks and cover parameter choices that we haven't found out. And if you have found it, yeah, okay, yes, question.
Okay, so this slide makes me question about the previous motivation about adding noise. So the previous motivation is basically saying that, okay, in addition to the noise from HDD, this is the mini batching part, you need additional noise, right, in adding to the weights. So now basically this says, okay, I can do these multiple samples of Monte Carlo estimate, right, which also will reduce the variance coming from the Monte Carlo sample for your theta. Okay, it won't sort of like reduce the variance coming from the mini batching, but it basically somehow, I guess, make the noise coming from Monte Carlo smaller. Okay, then you say this still works, so I start to question about the previous motivation.
Wait, what was the previous motivation again?
The previous,
What did you say, Thomas? I don't know. No. I mean, it's not about this is not about simply about more noise is better. It's really about like what you estimate. And actually here, one sample is actually a very crude estimate of all the expectations, but somehow it still works during training. But normally, if you can try to estimate your objective a bit more precisely, you should do a bit better.
I agree.
Yes.
But then why did Thomas actually mention our previous motivation?
So the previous motivation is anti-correlated noise injection paper?
Yeah, basically, how does this actually relate to the previous kind of
Yes.
noise injection thing?
So these noise injection things, they also work better if you use more samples. But typically you can only afford one sample because then people reject your method immediately, or it's more expensive than SGD. But essentially these noise injection methods, they compute a smooth version of your loss landscape, like a convolution with a Gaussian. And of course, if you can optimize the smooth one even better, it will work better. So
I think the word noise is wrong. Noise doesn't mean it's gonna get worse. Right? Noise means it's gonna get smooth.
exactly.
Does that make
Okay,
sense?
I think that makes sense.
Cool, all good. Let me just wrap up this hyperparameter and then tricks part with, yes, an iPhone cheat sheet. So how do you actually use it when you are doing your project in Python or in like PyTorch? We have basically made an official repository, basically an official implementation of iPhone for PyTorch. So very easy to install, just pip install iPhone-opt. And then to use it, just import it. It's basically just a standard PyTorch optimizer. And then here you see like the hyperparameters that you need to set up. We already explained how to set them up. And then during training, the first for loop, if you have all the compute you need, you have like hundreds of GPU, you just want to get the good stuff, you can use multiple samples, but it already works so well with one sample. And then maybe one thing that is a bit different compared to standard SED and then Adam optimizers, that here we are doing sample estimation, right? And then here we implement a context to temporarily basically draw and then use a weight sample, and then all the computation inside this context will be kind of carried out using this weight sample. And then there's this training goes to true. Basically, it's just to tell iPhone that you need to collect the gradient estimates towards the end. And then basically it's how actually the training is done. I mean, this inner part is basically the standard thing that you do in your deep learning pipelines, I guess. So it's really you can just use it as like standard like optimizer with just one additional context to draw the sample. And then during evaluation, there are two ways to approach things. You can do the correcting and then do the Bayesian predictions, and then in this case, you draw multiple samples to kind of estimate like a probabilistic output. And then again, use the same context, draw the weight samples, and then collect the output samples and do things with that. Or you could say, oh, drawing too many samples are like really costly. I just want to have a very fast inference, and then you just do the map inference, and then basically just take the mean, and then which is also the mode of your posterior, and then which is already stored in the model. So here you just do basically evaluate it directly, and then this gives you like the sample estimate at the mean of your posterior or the mode of your posterior. Yes, so that's kind of like the how to use it part, and then we'll see some examples, starting with maybe the most exciting one, what people get excited about, I guess, and it's the GPT-2 training. And then here we compare with LMW, I guess it's like the classical benchmark. And then we actually try different sizes, like just small, medium, large, or something like that. And we see that basically here we can really scale this up to decent size. Let's say it's kind of like 700 something M, it's kind of 0.7 B, maybe this is something people are more familiar about. And then we see that actually if we tune things correctly, and then Ivan can actually consistently kind of get something a bit better compared to NW. I guess different people care about that. And then also in terms of runtime, here we see that actually basically here we show where everything is at 12 and then 24 hours for the medium-sized models. And then we see that, okay, IMW is a bit faster, but then IMO is not that much slower. I think the overhead is always within 20%. And then that was with our research grade implementation. We are right now working on like a faster one that should hopefully further reduce this overhead. And then, of course, we show this is because this is what people care about these days somehow. It's not that this is the only thing we can do. And then we also do experiments, for example, like the classical ImageNet classification. It also works quite well. It's better than AdamW, and then we estimate later it's also a bit better than SCD, so yeah. And here we also show this, this is the reliability diagram. Basically, it kind of shows how well your training model is calibrated, or whether like the confidence level that is predicted makes sense. And then here, for example, we see the model trained by NW is actually overconfident. It says that, for example, when the model is 90% sure about the prediction, it's actually only 80% of the time correct. And then this basically shows that it's kind of overconfident. And then you see that basically, ideally, we want to have something like the diagonal, so everything matches, and then the thing's perfectly calibrated. And then we see basically the model trained by Ivan is actually clearly better calibrated, which is good, I guess. Okay, here's the big table with all the numbers you want to see. Oh, sorry, yes, please.
I forget to ask basically your GPT-2 figure. So your curve, or the red curve, is that the result from the mean estimate or from the ensemble?
That is a very good question. I think it's just mean, and actually if you actually spend the time to actually do the processing, maybe it's even better. And actually, yeah, I think it's mean, yeah.
Outside a question, so does that fit on a single GPU, or do you need several GPUs?
It's the same as you train. It's the same as you train using AdamW, not require too much more memory for doing that.
Because I was wondering, like, if you these days, like, if you train even bigger models, say, these ones that don't fit on a single GPU, then often you have this kind of complexity of using something like Accelerate or one of these frameworks. And I was wondering, like, if you would do that with I1, now that you have the sampling step, do you have any intuition how you would do this, right? Do you sample separately on the different GPUs, or do you need some parameter server that actually communicates the samples, and how do you do that?
This is actually a very good question. When we are trying, sorry.
So I would just say that I think you probably haven't tried it, but with Vaughan we were able to sell separate and different for our work very well, like that helped. So I imagine it would be the same.
We use different samples on the different GPUs, and that introduces the variance of here. It's like local reparameterization trick, people call it.
And also, it's actually helpful to actually, it can actually be helpful to use different noise on different machines, and then you actually get better results for free. But of course, you can do the class version and then just use the same noise everywhere. That was as intended. Yes. Oh, thanks. Okay, continue.
Sorry.
Yes. Oh, sorry. Please.
I have a very naive question just from seeing those graphs. The first one is when you know how to stop, because in some sense, Ivan is winning at like the last lap, right? Otherwise you wouldn't. And we also, I guess we're just seeing the mean of the validation. Does having the variance on validation helps in any way for a very slow feeling?
I did some experiment on fine tuning using, I guess, Adam with an Ivan trained model
Adam with an Adam trade model, and I've noticed a better generalization for the dataset that I tried on it. So I think there is a benefit with the variant. Also, I did also some additional experiment with iPhone, trying to disable the variants with and without the variants during fine tuning, and we can see there is a notable difference in the thing, and it seems like there is a better adaptability if the variant is used in the training. Does this answer the question?
No, but we can talk about it.
Okay.
You don't need to early stop actually. Maybe I can just say they're not saying it. Like early stopping for Adam, if you keep running Adam, at least for image classification, it goes like that. So it overfits after some time. But we show in the paper that if you keep running with Adam, it doesn't have the same behavior. So ultimately, it actually wins over SGD in that because of that reason. So the Bayesian thing is really doing is working.
Suggestion. I don't know if you know about the benchmark that we released. It's called MLCom. MLCom's benchmark is a set of basically models and data set pairs. So you can have an implementation in JAX or PyTorch, and you can run it on all the basically tasks, and you can benchmark it against like Adam W and a bunch of other implementations. So that would be a good basic point to see.
Yes, of course. Yes.
That they trust masses.
Yes.
We sign up for it, but we haven't had time.
Yeah, I think there was something. Yeah, there were some other things coming up. Yeah. But of course, that can be interesting. Yeah, sorry, you have something else.
I also had a very similar question. So you were talking about like a bunch of hyperparameters earlier.
Yes.
Like, I guess this is validation, or is it actually test? I don't actually know. I think these people say validation but actually mean test, right?
Probably yes.
Like you're not actually doing like select hyperparameters in validation and then test the data, right? Like how much does your hyperparameter selection influence this? Like how sort of sensitive is it to correct choice of these new hyperparameters like age and lambda that we talked about earlier?
And of course, it matters how you tune, like the parameter choice, of course, matters. For this, to be honest, because I didn't do this experiment myself, maybe somebody
or
can.
the other one, like any of these, right? It doesn't need to be GPT.
I mean, this is basically like any other, using any other optimizer, so you also somehow need to tune the hyperparameters. And of course, like the proper way would be to actually reserve like a validation set, and then you actually try to tune everything on that, and then basically run a test set, right? Yeah. Yeah, more, but I mean, some hyperparameters, I mean, you have two more, and one you can just set it to n, and the other thing, of course, yes. But then other thing is kind of always, I think it's always around like the range of 0.01 and 1, somewhere around.
Maybe in the same. So in the same vein of the previous question, have you looked at like scaling laws? I mean, people typically, they hypertune these parameters on the smaller models, fit that thing. I don't know if I believe it, but anyway, fit that thing and then use those directly for the bigger models. Have you done anything like that? And just try to create these kind of scaling laws for the hyperparameters as you go to bigger scale and see if those are reliable and easy to use for this method.
And so first of all, we have already tried on, you see, like different kind of like size of models.
Yeah.
And then we have been, I think we are like doing something. Yes. The follow-up would actually to scale this even higher.
It's actually for the GPT-2 experiments, we follow the common experience in Adam W, that how they scale the render rate, and we scale as they scale, and I will still works very good. And for the other parameters, we just keep keep the larger models the same way the GPT-2 small one, and it seems to be good.
Okay, so you haven't tuned it for the light one, you just choose the same values
Yeah,
for smaller ones.
we didn't spend that much time tuning the parameters.
It might make sense to try to fit the curve, because sometimes they're not the same. I know like for the beta 1, beta 2, they tend to change at larger scale, but like you can, usually you just train a bunch of smaller models, fit the curve, and predict what the beta 1, beta 2 should be for the larger scale, and it tends to gain a little bit out of that.
Yes, thanks a lot. And there's no reason that I cannot go higher, of course, if we have the computation resource. Okay, let's continue. I think I've already explained this slide. Okay, 5 minutes. Okay, so yeah, here, yeah, and the number shows that Ivan works, and then it's very nice. And then you also have like this uncertainty matrix, like all the uncertainty metrics you want. And then basically this actually covers different different data sets and different models in different size and scale. And then we see that consistently Ivan can work quite well. And then there's also this Ivan at mean, which is the map inference, and then there the accuracy is also quite good. But then in terms of uncertainty estimation, I guess in terms of ECE, it's no longer as good, but then it's still like not worse than HDD or something. Okay, and also we can also check out, for example, like the OOD case, and then here we have the model trained on in-domain and cipher-10 samples, and then we ask them to make predictions on something that is completely irrelevant. In this case, is the street view house numbers, like numbers in the wild, and then you would ideally want the model to say, I don't know, and then just have very uncertain predictions, and then this unfortunately not the case directly if you train with HDD. And then on the other hand, for like Bayes-Duality Workshop, at least the common implementation that you can find online, and it's the other way around. Everything is uncertain, which is good for OOD, but then for the in-domain case, you are not doing the prediction as well as it should be. And then other methods, including ION, works a bit better, and then especially here, ION, you see that it's actually quite certain when it should be for the in-domain case, and quite uncertain also when it should be for the OOD case. And also, I just mentioned this actually, like the project started really long ago in 2021, and there was already like a very old variant of IVON, which is also called IVON, that wins the nearest challenge for approximate Bayesian inference. We are the first place, Team Möllenhoff. And then we revisited this thing, and then also we tried out and to see if we somehow have like some notable regression. And so the good thing is, the good news basically for MetaMIS and UCI, the results become even better. And then the strange thing is basically for cipher-10, slightly worse, but still like we are better than the other alternatives. I think it's just like because the old version actually we use some tricks, for example, like this. Diagonal damping, and then the private parameters are chosen much more poorly. Somehow we still win the first place. I don't know why. Anyway, and so this covers kind of like the like the common things that the community has been focusing on. Is this everything? And you will see in the afternoon that it's not. There are many more things that you can do. And then basically doing all this not just about uncertainty estimation or better generalization. There are many other things that you can do with this. I mean, you went through all this trouble of doing the proper Bayesian formulation and everything. So yeah, there are many other things. You'll see that in the afternoon. Since we don't have time, I just skip them. I mean, you'll see there's something about model merging. There's also something about better understanding the model from like the data perspective, from the sensitivity analysis perspective. You will see all this in detail in the afternoon. And to conclude, yes. So yeah, there are many other things that you can do apart from just doing uncertainty estimation. You'll see this in the afternoon talks. But of course, to do all these amazing other things, you need a Bayesian method that actually should work. And then IVON, it can be such a candidate. And yes, Ivan works, and then you can scale this up for large enough models such as GPT-2. And yeah, I mean, Ivan also worked for uncertainty estimation. We won the first place for the challenge. And yes, what are you waiting for? Install it right now. It's free. Thanks a lot for your attention. Yes. And there's actually another case. We have a demo, but I guess we don't have time. Maybe you can show it in the afternoon or something. Yeah.
Yeah, just a quick question. So yesterday Rio was saying that in the context of these infinite width limits, right, like this mu-p and stuff, you have a lot of methods that have kind of the same parameterization, but he said specifically Ivan has kind of a different one, which I didn't quite manage to understand yesterday, so I was wondering whether you could kind of maybe comment on this now that we understand Ivan better.
To be honest, I also didn't really understand yesterday. Maybe someone else can comment on this, or maybe, okay, so it seems like it's actually a very, very advanced topic, yeah. Yeah.
Okay, thanks for the talk. So I have a very long time thinking about, the connections between, for example, say stochastic gradient long dynamics and also basically mean-differential inference. They are actually quite similar, although there are some important differences. So your method here compared to Adam W, right, is mainly about how you change the conditioning, right? Instead of using square root of this this age accumulation, you're using just age directly, right? So people have been actually doing similar things about trying to convert some kind of optimization methods like Adam to SGN sensing methods. They're using the same square root kind of conditioning, but it doesn't seem to work that well. So my question is actually, do you think that your new conditioning method data, the success here, can be transferred to the SGN CMC world?
I don't think I'm expert enough to answer this. Maybe MT, you have something.
Yes and no, actually. So there's a gap because so you can actually this noise is added in the parameter, and as I said, duality, you can push the noise outside to the data, to the gradients. So you could actually write a version where you run noisy gradients, right? I don't know if you see my point. The noise in the parameter can be pushed through Taylor approximation, let's say, to the noise in gradient. And you could see this as an SGU and CMC, but it's not really estimating the stationary distribution, right? So there's very simple differences that come in. So if you really wanted to randomly explore the posterior, it really doesn't. But it helps you to bridge the gap. So in 2018, actually, we were thinking about this, and I think also Jasper and other people also tried this thing, but we don't know right now. The deterministic world and MCMC world still remains quite far in that sense. But I think Navish is here, and we've been talking about this with him and his supervisor, also talking with optimization folks to see if there's a way to, because there's a lot of work on like mirror descent and doing stochastic gradient, like SGLD style mirror descent, which is where we're getting to in this. But we don't know how, when the converging distribution is the true posterior, that gap still exists.
So let's thank the speakers again.
So just in the second part, maybe the hope is to try to convince or show you some examples of this sensitivity perturbation duality that I talked about in the first part. It makes less sense in the abstract form, but it was on purpose that I start with that and try to show you examples, and maybe that way you get a feel of what we've been trying, and hopefully it will be useful for you in some way. So as I said in the beginning, I said trustworthy system, right? The reliable systems, and designing such system, it also comes down to understanding what the system is made up of, right? So if you know that there is a system and it has many parts in it, what does each part contribute to? you can go inside. So I love this GIF that I stole from some website. But basically, you can go in and you can you can do some intervention, right? You can stop some parts and you can observe the effect in the outside, what happens, and this is how you can figure out. Maybe things are non-linear and non-identifiable sometimes, but at least this is how you will proceed to figure things out and know those properties of the system. So, so once you know what parts contribute to what, then you also know if something goes wrong or something needs to be fixed, then what needs to be fixed, or at least how to go about that. So that's what I mean, like when you want reliable system, you're thinking about where the knowledge is stored in the model, and then you want to reshape that knowledge and transfer and adapt it eventually. And all of these questions are rooted in perturbation and sensitivity. Right, so I'm bringing down all of this to this simple idea that that we should be able to solve, make a trustworthy system or an adaptive system, incremental learning, continual lifelong learning, all sorts of things, if we actually paid attention or understood how to measure sensitivity to certain perturbation. Right, and not know how to perturb and what to perturb, and how to reuse this thing. That's kind of how we figure out the math. But the concept is very simple. We measure sensitivity to perturbation. And this notion, of course, I can call it sensitivity analysis. I could also call it uncertainty estimation, but they're kind of the same thing. And the bigger word for this that I found, and so I chose the word duality, because instead of representing things in terms of, you know, the system as you see what the system is, like think about model parameter, now we are thinking about perturbation. So we are characterizing the system in terms of sensitivity. And this is a dual view. Okay, and you know, I think in many fields when you talk about duality, you will see that the dual space is somehow is sensitivity and the primal space is not. Like think of like Fourier transform or wavelet transform, like all the orthogonalization things that you do in signal processing. You could have a matrix, but matrix doesn't tell you everything. But if you think about a singular value decomposition of that matrix, it tells you what it's made up of. So you can write the matrix as a sum over all the eigenvectors, outer products, right? And you know that there are dominant eigenvectors that contribute a lot to the system. So it's really about writing parameter as some kind of sum of some components that are being built. You will see that if you start to think like this, you cannot unsee this. So we think that this is really fundamental, and we can debate it, and we can question it, but this is the hypothesis being put forward. So I think when it comes to machine learning system, this is one such result that I think is general enough. It may not be everything, like it holds for exponential family, it holds for certain kind of training algorithm, but this is general enough to start thinking about these things from first principles point of view. So we say, well, the simplest kind of thing is that loss functions made up of data points, and then when you are learning, many learning algorithms are trying to learn natural parameters through natural gradients. So I know that every natural parameter is made up of some kind of, you know, weighted sum of natural gradients. It lies in the span of this. So you could see that somehow SVD is kind of flavor. Like if you have a matrix X, its columns are spanned by certain eigenvectors. So that X lies in the span of those eigenvectors. I'm actually saying very similar things here. I'm saying natural parameter lies in the span of natural gradient. So certain natural gradients actually do more things, others don't, less. Okay, so we'll try to see some examples of this in several ways. So I think some of the things that I'm going to show, they're basically based on this thing that's written here. So these local parameters, so when I say local parameters, I mean lambda tildes. Okay, so remember, whenever you have tilde, then it's natural gradient. Okay, so lambda tilde And sometimes it's per data example, but you can also think about this whole thing as a natural gradient of the loss. So that will also be lambda tilde, but no, with no I there. So the natural gradient is made up of this is like sum over natural gradients, and you can basically try to add and remove these things from the sum. So addition and subtraction should somehow help us understand how much lambda changes, right? Now it is only a local effect, and then there's a question on how to do this globally, and maybe in the end we'll see the difficulty of it. But nevertheless, I feel this is a good starting point to start thinking about those things. So what we want to actually do, that we know that these algorithms, and I think Adam asked this question already, so I said that, but all these algorithms, they're related, sorry, this algorithm is related to all the other algorithms that I showed in that table. So this is general enough for me to start understanding sensitivity of those algorithms through understanding the sensitivity of this equation. Okay, so basically, we want to kind of understand, I think it's not written very well, but this translates to measuring the sensitivity of the trajectory of a variety of algorithms is what I want to say. Okay, and used to analyze their behavior. Okay, sorry, it took a few minutes to say this, but I just wanted, again, the main point to be there. But let's go to example where it becomes a little bit more clear. So the first work, I think model merging was, I found it 1 year ago. And this workshop, actually, I didn't know about this field. So it was exciting for me because I realized, oh, it's actually simpler than continual learning and maybe easier to get the LLM folks on board. So I talk about this now first, even though this was the most recent work. And Nico is this amazing guy who's not here, who's supposed to be here, but he has an LLM conference to attend, and he'll come here next week. So he should be presenting this part, but I'm filling in for him. So just think of me as Nico. But he can make anything work, by the way. He's the one who did the first GPT-2 training without any effort and said, oh, it works. Yeah. So he's been working on this model merging, and it's with several other people, and also Thomas. But the main point here is these two papers. The first one is published. The second one, Ugo will actually come and give part of this talk. But here we're trying to connect the inaccuracy of the model merging to gradient mismatch. So that's kind of the dual view. You see that that lambda tilde becomes gradient, and then you can start to talk about this inaccuracy of the model merging through the dual view. It just makes more sense. And you can reduce it if you use better posterior. So that's kind of what we're going to do. And do you see this this whiteboard? You've seen it somewhere. It's right there in front of you. And this was exactly a year ago. So I actually saw Nico's talk, and I immediately knew what problems are in their model merging things. It's actually EWC, if you kind of, you probably know, right? Razvan is here, but here I actually said, like somewhere here, I said, oh, it's all just Bayesian. This is just approximate Bayes. Okay, so I literally wrote the whole paper on that board, and it's all these questions are also what's later got written in there. So it just took 10 minutes to do all this. Okay, with all that boasting, let me actually talk about something. So in my tutorial, I said knowledge addition. And so model merging is kind of addition of knowledge. Basically, you have a parameter theta1 that's trained on the data d1, and parameter theta2 that's trained on d2. And our goal is to get to a model that's trained on both. Okay, so I call it theta1 plus 2, but the plus is inside the parameter, it's under the parameter, right? So I have theta1 and theta2, and I want to get to theta1 plus 2 somehow. And we are going to look into this very local perturbation. So we are thinking about fine tuning, which is a large pre-trained model, and theta1, theta2 are just kind of small perturbation to it because of the data, small data. So like think of like model LLM trained on English, and then we train theta1 on Japanese and theta2 in Chinese, right? And then these are very small perturbation to it. So it's very nice problem to study because we think addition should kind of work here because they're not that far, so they're more or less linear. And I think that's why they are actually working and people are quite excited. So the weirdest thing, right, so people do this, sorry, I don't have all the citation here. If Nico was here, he would probably do a much better job in citing these papers, but simplest way that you can do it, and people do it, is that they just add the parameters. And this is insane, right? And people say, what the hell, why should it work? Like, that doesn't make any sense. So alpha 1, alpha 2 is just scalars, and you just multiply by scalar, and you just add it. And then they come up with like, oh, linear mode connectivity, I mean, everything is close by, low loss, test loss. I don't know, you know, maybe this is going way too fancy. There should be a simpler answer. I mean, if they are like close by, addition should work, is what you would think, right? Then people do something more fancy. So this is like Fisher averaging. I've written H, but because I like Hessians more than Fisher, but you can think of H as Fisher. This is like EWC actually in the end, but you know, you weigh things by something, and if you were at the tutorial, you kind of see where I'm going. You could already see I wrote this equation for sample average already. So right, so this we would expect this should work better slightly, but I mean it's not clear when you look at this. You say, why should it work better? Oh, because you know, weight uncertainty. Because if some things you're more uncertain about, then you should weigh them by something. You could do this logic and fine. And then some people say, yeah, Bayesian should be better, but how do I estimate Hessian? This and that is just lots of things, right? I don't know what exactly is the answer, but it seems better. Did they do this crazy thing in LLM, which looks, so this is what Nico was presenting last year. And I looked at it and I said, oh, I know what this is. But what they're actually doing here is that they're taking the theta 2 because it was pre-trained on an LLM. You subtract the LLM. So now this is new knowledge. You see, subtraction kind of remove the old knowledge. And now this is new knowledge. It's like innovation. And then I add the innovation. So addition makes sense in the new knowledge space because the redundant things to be subtracted because double counted otherwise. And then you add back the theta LLM, right? So they're doing, they call it task arithmetic. Good name. Yeah? I love this name. But I mean, method is like, well, we just did it and it worked, right? But why does it work? So why should any of this work? Right? And you can think about this. And I don't know if anybody wants to say anything. Happy to hear about this. If anybody has a new opinion why this should work? Not work? Okay, good. So I have a lot of opinions. So when I saw this, I said, oh, you know, I'm Bayesian. So this is just approximate Bayes, like a root Bayesian. I came in. I say, oh, these additions, they're basically just multiplication of Gaussians. Like that's the first thing you think about. So you say, oh, theta 1, theta 2. I can think about it as like multiplying two Gaussians whose means are theta 1 and theta 2. Basically raise it to the power alpha. So covariance is identity. You could work this equation. I think I tried to do this in my tutorial, but you know, you can do it now. And when you do this Hessian thing, can you guess what's changed in that Gaussian?
Covariance.
Yes, somebody not ABI team. Covariance. So covariance should be set to what? Yes, Hessian inverse. Roshni has read our papers. Nice. Thank you. So, right. So do you see that as a Bayesian, why would I think this works better? Is because you go from a simpler Gaussian to a more flexible Gaussian. It has more information somehow, right? That's the intuition. And can you guess how this comes out to be? So if you attended Siddharth's talk yesterday.
You don't like EP names.
Sorry?
You don't like the word EP.
I hate it, yeah. Go on.
Like, this is kind of like constructing vector graph. Right?
Yeah. But again, I think if if people have like really said EP to you when you're growing up, then it's like extremist ideologies. I'm sorry for you, but it's your parents' fault. It's very simple actually. You think of this as prior, right? LLM is the prior, so you just divide it by that, and then you add back the prior. Actually, this is called Bayesian committee machine. That's 96. If you look in the GP paper, a GP book, you'll find this expression. But it goes before. It's the work of Mutambara actually. I actually learned about this after my master's when I worked in a company that was doing plant diagnosis and stuff. So we do distributed, information fusion with Kalman filters. That this is actually how you do it, and this is very common actually. There's a whole field called Big Bayes that was based on this. So it makes sense, right? All of this makes sense. So it seems like to me that better posterior should give better merging, and I could stop my work here and call it a Bayesian day and just go on with my life, right? But I didn't want to take this route to explain it to them, because this is kind of explaining away like, oh, it works better because better posterior should give better result. But I don't have a proof, why should it? Like, suppose I didn't know that this was multiplication of Gaussian. Can I still show that somehow this H that I added, it gives me better result? Okay, so I wrote down that 10-minute bits that I wrote here for them, but it was thinking about Bayes and addition that brought me to that answer, is what I want to say. Okay, so, there's going to be a lot of math now, but, make it more concrete what I mean by dual. So let's start with a very simple problem. Let's say theta1 this is L1, it is on the data 1. So D1 is somehow inside this, and I put an L2 regularizer here because that's needed to write the dual view. So it's needed. So let's do the dual thing. Like, if suppose that L2 regularizer were there, then if you take the stationary point of this, right, then the gradient is 0, right? So you take gradient of this, you get that. You take gradient of this, you get theta 1. So this is theta 1 is the minimum, so I get this relationship. Anything wrong? I hope I have not made any mistakes. But if this is correct, then I know that theta 1 is actually just the gradient, negative of gradient. So you see, dual view is like writing the parameter, it's actually the gradient. A stationary condition tells you that when you have a regularizer in this case. But this is, you don't have to believe me right now, but I'm just saying that this is a special case when you take the equation that I showed you. If you use a Gaussian with only the mean as free, that equation will turn into this equation. Okay, so not doing that derivation here because you don't have to know anything Bayesian to be believed about, or to believe this equation, right? So everybody's good at this, right? So I just said that this is a dual view as a footnote. But Thomas actually gave a tutorial on writing theta 1 as, he called it alpha, but it's error times so in linear model, this will be like just a feature. So it kind of tells you every feature contributes something to your model parameter. The features that contribute more are more important somehow. So that's how representative theorem works. This is just a representative theorem in the convex case. Okay, and this is a special case, so this is what I just said. So let's forget about this if you don't like it, but that's how I came up with this. So let's say theta 1 has the same thing, so I could write the same thing for theta 2, right? Theta 2 is also made up of this, and then I could write the same thing about theta 1 plus 2. Right, now you start to see that I'm representing the model by the gradient. So this gradient evaluated at theta 1, this gradient evaluated at theta 2, but this one is evaluated at theta 1 plus 2 on the two losses, right? So if I want to know the difference between theta 1 plus 2 and theta 1 plus theta 2, then I know, right? If I subtract this guy from this guy, so the difference is that this was evaluated at 1 plus 2 and this is evaluated at 1. And this is evaluated at 1 plus 2 and this is evaluated at 2. So from here you can actually see that there's two data sets. And they're supposed to, so this model is supposed to do something on this data set, but it's different from what the joint model would do. So there's some discrepancy, mismatch in the gradient, right? This gradient and this gradient are different, and this gradient and this gradient are different. So gradient mismatch over L1 on D1 between these two guys, and mismatch between these two guys. So it's like theta 1 and theta 2 are different, but they're different through this joint model. It's telling somehow they need to coordinate and align their gradients so that they do the right thing. That makes sense? It's a very, very simple thing to say. Let's rewrite it, right? So that's what happens when you do parameter addition, you get mismatch in the gradients, the two of them, okay? And then you say, oh, well, so this is pretty bad, but how can I improve it? But if you want to improve it, let's minimize this mismatch. And you can minimize it just by using Taylor approximation. Okay? Is this clear? So difference between the two gradients, just the Hessian. So second derivative of this function is the Hessian times the difference between the parameters. The same thing here. Does that make sense? And if you rearrange it, you'll get Fisher merging, Hessian merging. So now you could be completely convinced that if I use a better posterior distribution, it gives me better results. So discuss. Is this good? So I didn't do anything Bayesian here. Huh? I just showed you that, yeah, better posterior gives me better, yeah.
Thank you. So I guess another way of looking at this is minimizing the KL divergence between theta 1 plus 2 and each of them individually, right?
Exactly. That's just the difference.
If you do the theta, you get Fisher again.
Exactly. So
like broadly speaking, this is kind of like distillation. If you
yeah. In the next part of the talk, I'll show you this also distillation. Okay. They're also doing the same thing. Okay. Yeah. So you're exactly right, and you're a little bit ahead because you work with duality a lot. So you know that when you take the derivative of divergences, you get difference between gradients. I think Frank Nielsen knows this the most. But the derivative of divergences with respect to dual parameter gives the difference with respect to the primal parameter. Here, Euclidean distance, so it's both theta, so it's just the difference in gradient. But if you can write the same calculation in the Gaussian with the Hessian kind of covariance space, but it will repeat. So that's how you get this. This one is, if you started with a Gaussian where mean and covariance both are known, and you took the gradients, you'll get the difference between the natural parameters, which will be like difference in natural gradient. I don't know if I'm going through you, but there's a bigger principle here. Anyway, I will skip that part for later because we're only working with theta space here, and then we went to like theta times h space where things are somehow added. So it may not make much sense right away. But let's just think about, look, does it actually work in practice, right? That's what you care about. So this is an example of kind of showing that this gradient mismatch, it correlates with the true test error. So here, what we plotted is some kind of norm of gradient mismatch. This is for a fine-tuning procedure. And here you do like brute force retraining. So kind of tells you that each of this model, it gets reduction. When gradient mismatch is reduced, the test error is also reduced. Okay, does it make sense? So like reducing the gradient mismatch also leads to improvements in the test error is what it's showing you. Okay, so from here, I think you can already make this big jump about like how do we build trustworthy systems, right? You just give me a second. So trustworthy systems, you want to be asking this question like, what if I merge all this model? What would happen? You don't have to retrain. Again, with all of this data, you can simply do the simple merging, and that already tells you without retraining what would happen. So this will be a recurring thing. Yeah.
So I was wondering, maybe I just missed it, but because you keep saying like it's fine tuning and that's what you're wrong, is this like the assumption because you don't want to deal with like permutation symmetry and stuff like that?
Yeah, something like that. Yes. Yeah, it has to be close enough so that these calculations are kind of, they make sense. Simple calculations, right? You haven't. Yeah.
So I think this theme of things being close enough will come over and over again, because that's, how do you define these closeness? How do you know if things, like you gave the example of Japanese and Chinese, if I would have to guess, those would not be close enough, because to me Japanese and Chinese feel very different. I don't know, are they, or?
Yeah, it depends on which model you're using, right? But I think the gradient mismatch actually gives you that. So if you actually train the model, like so you could do this experiment, right? You could actually train theta 1 plus 2 on both Japanese and Chinese, and then you can look into the difference between the two. And that's kind of what I'm showing in the next one, right? So
yeah, but that implies you training on a joint which you kind of want to avoid.
exactly, yeah. So you cannot do it, but beforehand you can look at the proxy, right? So that's kind of what I showed you.
Which is the Taylor expansion, which only holds locally. So
exactly. So yeah. So you cannot do it right now. Yeah. But there's more to story, more coming. This is the problem we need to solve. You're exactly pinpointing the right problem. But this is the first step. You look locally in this problem where things are local, makes sense, and that's why it all works. There's no magic here, right? When you start to apply this to continual learning, it's not going to work. Federated learning it'll stop working. Okay, so maybe last thing, and I don't have much time because I want to give it to Ugo, but this blew my mind. But I haven't explained what influences are. But so let's just go back and like think about like, like I showed this trustworthy AI system, right? And I said, oh, you can train models by removing some data, and you can retrain, and you get multiple copies of this model, which differ by slightly little thing. You can actually think about model merging, like let's say you have a pre-trained model, right? And you did fine tuning with Japanese, and then you did fine tuning with Chinese, and then you did fine tuning with Spanish, and you got different perturbations of your model merging. So it turns out that actually if you do it right, which is our method, if you do the addition subtraction in the right space, then actually this also means that you're doing this addition and removing of the data. This is insane. It should be a much bigger deal, but you have to appreciate influence function first, so maybe you don't realize it, but this is huge. So it may not make much sense right now, but just take this later and we can talk about this. So let's say we want to remove toxic behavior. So let's go to toxic behavior. So let's say I want to remove Reddit from my model. What I could do is I can fine tune just on Reddit. Okay? I can fine tune, and then I can subtract that knowledge from the LLM. Okay? It's good? So basically that's what I've written here. LLM minus 1. The 1 is Reddit. And you can do it if you apply it to that rule that I just showed you. It's this, so theta 1 minus LLM, so this is the new thing. So so what is, I should have written minus inside. So theta LLM minus theta 1, think of it like that. So I'm removing the Reddit knowledge from it, and I'm kind of taking 1 Newton kind of step to subtract this from my theta LLM, okay? If you do task arithmetic, this preconditioner will be missing, right? But actually, if you did this, then with this preconditioner, you can, what I've done here is I've just pushed this H inside, okay? Maybe it doesn't make sense to you right now why I'm so excited about this, but you can actually see that this is a subtraction in the natural parameter space. It's S times theta. S is the position. This is Laplace approximation, so Alex should be happy. So H is the Hessian, which is the position. And H times theta, these things are additive. You can add, subtract in that space, right? I think maybe Thomas, this is first time I'm writing it like this, so you also see it first time. But if you actually applied this on a linear model, you will see that it's exactly equivalent to influence function. This is first time. I don't think anybody's ever done this because, Cook didn't know LLM. So Robert Cook, who wrote this in 72, jackknife people didn't know it, right? But isn't this incredible? You want to remove data, so you can actually train a model on that data that you want to remove, and then you can subtract it. But if you did the subtraction right, it actually does kind of the right thing.
I'm a bit confused. So the data, so let's say Reddit data, so sigma theta LLM was all of internet, which includes Reddit.
Yes.
So how do you,
I
what
hope,
is
yeah.
theta 1? What is theta 1 being extra trained on, like one more time being trained on?
Yeah, you start from LLM, fine tune on Reddit.
But Reddit is already there.
Yeah. But you fine tune on Reddit. Yeah. But like you could think of like it's a different copy of Reddit, right? Maybe OpenAI has a different copy, slightly different. So you again train on it, fine tune on it, and you subtract it from it. You can actually do this on linear model as well. You will recover. This is exact for linear model. But I'm just saying that this thing looks weird, right? You say, oh, subtracting parameter doesn't make sense. Adding parameters actually does make sense. That's what I'm trying to say. It makes sense up to some linear thing, small region. So these calculations, they're not meaningless. Like LLM community is not just playing with noise. You know, they've got something right. But you have to understand the more underlying principle that it's the right space to do addition in. If you don't know about this, then you will be doing whatever, you know, and not know the importance of it.
Maybe I'm going to read your assignment. So, in my opinion, machine learning is basically the kind of similar problem as continual learning. And if you do unlearning for one data point, okay, then it's essentially approximation to data influence. Okay, so my claim here is any continual learning method, at least with the Bayesian interpretation with that, can be used as unlearning problem, and also it can reach to a corresponding data influence function.
Yeah, that's true.
So I guess this is maybe, let's say, one instance of, let's say, the all possible Bayesian version of data influence.
Yeah, that is true. But this kind of derived in completely non-Bayesian way, so that's the excitement here. I know Bayesians shouldn't be excited, but then Bayesians should be excited because this is approximately Bayesian, right? It's not truly Bayesian, and you still have certain properties that are being preserved of doing that thing. You are completely free to not be excited about it. Good for you. But I'll tell you that you'll come around someday.
Just trying to connect this. You to the natural parameter addition, you made a comment just a minute ago that H theta is the same as SM. And trying to map it onto the whole VLR framework, it seems like there's a mismatch because in the VLR framework you've got a distribution over theta. So M and H there or S are the mean and variance of theta, whereas here these are the
it's the same.
It's the curvature of the loss, and theta is just appearance to that.
It's exactly the same thing. So theta 1 is the mean, and H1 is the precision, which turns out to be also the Hessian of the loss through the optimality condition. We could talk about this offline.
Yeah. Okay.
So what's the H LLM minus 1?
This is the Hessian on the LLM minus the loss of the Reddit, and then you compute Hessians. So loss of LLM minus the loss of Reddit. Hopefully it's like with loss without the Reddit data, and then you take the Hessian of that.
Hessian with respect to theta LLM though.
It is with respect to theta LLM. Yes. You don't need to compute it in like one and then yeah.
So how do you compute H inverse of a large language model?
Yeah.
Any tricks?
Yes, we don't. So we do I1 like things. So we compute diagonal and all of the results in the paper with diagonal. So they're basically you do I1, you get an H vector, and then you use that. That makes sense? I mean, in this paper, we didn't even do that. We just used square gradient with a small mini bat size, which turns out to be also a good estimator. Mini bat size has to be small. And I could tell you later why that is the case. Sorry, there was, yeah.
So, by the same principle, you can also learn Reddit, right? So if you do the opposite, you learn Reddit. So
Yeah, sorry, so let me just stop you, and I did forget to tell Yingzhen, but I hate the word unlearning.
Okay. So
because the unlearning is wrong. It's data removal, is what you do.
Okay, so you can do data addition, right? So let's say you repeat that for all subsets of data. So what happens? Does it cancel out? You get the same model back?
No, these are local effects, right? So you can only, again, I said, you can only do certain things be undone. Certain things that were done recently, they will be undone.
So my point is that, okay, take Reddit, Wikipedia, just fine-tune separate language models, calculate the same Hessian, do the same operation, but do with a plus sign.
Yeah.
Model. So what do you get at the end?
It does something, yes. It knows something, but I don't know what is better, right? So
in terms of log perplexity,
I don't know. It'll do something different, yes. But I don't know if it really can do the right thing that you want, because that's kind of hard, right? It's a good question, sorry, I cannot answer it. But it's a good question too. I think there's one also.
So if I want you to remove data from your model, maybe I want to check that you indeed remove it from your model. Is there a way to quantify that?
Sorry, can you repeat that?
If I want you to remove any information you have from me in your models, I might want to double check it. Is there a way to quantify the amount of information we remove?
But that's what this is, right? So it's this kind of you.
It is a principle. I want to come and check like how many information are left. Almost zero.
Yeah, so there's no way to do it without doing it. So you subtract things and then, so these are first order effects, right? So please remember in mind, so this fine tuning, it does only very local first order effects. First order, second order, depending on, so if you did task arithmetic, it's first order because it's just the mean and first order Taylor expansion. If you did Gaussian with mean and covariance, like this H theta, this is second order effect. But that's where it is. You cannot tell more than that without doing few more gradient steps. And that's what kind of we've been working on. Maybe next year, this will be out, yeah.
So I had another question. So as you said, this is just sort of like second order, up to second order Taylor that everything works. So when like model merging came out, people got really excited, and I think they're kind of like reading too much into it. I wonder, like, have you done experiments where you play with the size of the model? Because my intuition has always been that the reason this works, because like everything is over parameterized, and that's when all of this first order, second order kind of approximations are quite decent. But if I have the model smaller, then like all of this would break, even for what we think are quite similar things. So I don't know if you have like, if anyone has ever played of like, when does this kick in and when does it kind of break?
We haven't, right? We haven't, yeah. But I completely agree with you, actually. It should be like that, and I was going to say something, but I forgot. But yeah, it should. I mean, so what I want to say, it's very easy to break it. Okay, you could break it by just like running too long or something like that, right? Catastrophic forgetting. I think somebody wrote a paper on that some time ago.
I just sort of like an opinion. So then, in your opinion, with like the big models, GPT-4, whatever, are they still in this over-parameterized regime? Because if you just think of data versus model size, they might or might not be, but I wonder, like, if we're building all of this machinery that relies on over-parameterization, is it going to be useful at scale or not? I don't have an answer, I'm just curious.
Yeah, I don't have an answer either, actually. I think it's okay. I think it's just that if you have very big model, then it's very difficult to add and subtract things from it. That's kind of what you get, right? You got something that knows so much, and it has the capacity, but then it's also for this reason that it's not, things are entangled in a very weird way. So addition subtraction doesn't work. So you need to retrain. So you will, the bigger the model is, the higher the cost of, the more you need to retrain it. It's a cost that, they don't want to do it, that's why. Sorry, but.
So
does it not matter what method was used to fine tune theta 1? Like was it first order, second order method? Which method was used?
It doesn't matter that much, as long as like it shouldn't matter.
Nearby.
Yeah, as long as it's generalizing well somehow, so they are in a similar minima. So you could use SGD, and if it still gets to the solution that you use if you use Newton method, then it doesn't matter as long as they're at the same place. Is what I would say, but it may matter. I cannot say for sure. So okay, so I'll skip this thing. It just basically says that alpha doesn't matter because you use this Hessian scaling. So with that, I want to give it to Ugo, who'll talk about what is the goal of all of this, like how to set alphas.
Thank you. I'm Ugo Monsom. I'm a postdoc at Emtiyaz group, and so I tried to continue this model merging project by Nico and Thomas, and well, you will see that alpha actually matters. So what is the goal of model merging? Well, so you could see here we have like three losses, and the star mark their minima. So when we are doing model merging, we're actually trying to approximate the following objective, which is basically the weighted sum of all the losses. So basically, we are using this alpha to weight the data contribution to the joint model. So the question is, how do we set alpha? Does it matter? Usually in model merging papers, I think they're trying to weight equally all the models. So you end up with this black star, which is basically in this case, it will be set to 0.33 for all three of the losses. But ideally, what you want is to be able to adapt to new situations. So then having just one model with one set of alpha then is not enough, because maybe your downstream task needs that you pay more attention to a specific set of data, or basically putting a bigger alpha on the contribution of that model to the merge model, or simply you want to know how these data basically interact between each other through these models. So what we propose is that we should actually think of model merging as exploring different models. So we should actually consider all possible alpha values, and this is related to, well, my previous field, multi-objective optimization. So all of these theta alpha are actually part of a set that is called a Pareto set. So all of these theta alpha are the optimal solutions for these for the previous. If you solve this objective with each with different alphas, then all theta alphas live in this Pareto set, and we think that we should actually try to estimate this set through basically model merging. And what they encode is basically each one of them is a different trade-off between your models, a different trade-off of the data. So that means that we should think about that some models, well in this case, the data may not be compatible. For example, you are training your LLM in, if you train it on English and German, then we know from linguistics that they are kind of close. So if you optimize for one, maybe it's also beneficial when you do optimization for the other. So maybe it's much easier to obtain a model that performs well on both. But if you go, for example, on languages that are very far apart, for example, like it could be German and Japanese, then maybe matters more this kind of trade-off, and then you need to be more careful how you set your alpha values to try to get the model that you want. So here I just did like the the previous objective that I show, I actually compute for different alphas. And as you can see, it doesn't, so the alphas are drawn uniformly, but as you can see, here each point represents a different set of parameters for like a sort of like a two-dimensional, just like a toy model. And as you can see, although I draw alpha uniformly, they don't look uniform, right? So if you see on this line, is only if I go from here to here, like if I set alpha 0 and I give all the way to model 2 and I ignore model 3, and then I go like one that weights model 2 and model 1 equally, you see that that is not, so from 0 to 0.5, there is a bigger distance than if I go from this to here. So they are not, like, you see that there is some kind of trade-off. And the interesting thing is that we think that methods like the averaging are completely ignoring this situation. This also is, of course, related in some way to Bayes, and you could also see that instead of solving the previous objective that I showed, if you show the variational version, then you're trying to get this P of alpha. But we know from Bayes that if you want to approximate this, we can just do an aggregation of the individuals. I just learned, sorry, I do, for example, I1 on each objective. I obtain like a posterior, and then I just can weight the posterior, which is this multiplication will be basically addition of data, and this is how it's related also to model merging. So our claim with this is that we need to think of not only exploring different values of alpha, but also choosing better posterior approximations to do this. And through this, we will obtain, of course, like a better merge model. So as MT was showing that if you choose to learn only the mean with a constant covariance, so you're using an isotropic Gaussian, this is basically the what is called parameter averaging, and the mesh in red is the estimated parameters of, well, using this parameter averaging. And as you can see, there is a big difference between, for example, if the diamonds are in black and red are showing the same point of, like, for the same alpha values, the same point. And as you can see, there is a big difference. For example, in 0.6, they are very far apart, not so much for 0.8. But you see that parameter averaging just assumes that these theta values are also uniformly like spread in this parameter space. So we can also go like higher and do a better job by learning, for example, also the covariance matrix. So this will be our inverse Hessian. So here you see that it already starts looking much better. So we get these points are much closer. And if we keep doing this of using a better posterior, then we can, for example, get closer to the true shape of the of the original. So here we use a mixture of Gaussians, and we see that this already is doing a great job, but there's still some I don't know, is there any question? I should maybe slow down a bit. I don't know how much time I have. Okay, so then I will go through so this is just an example. So we use MNIST with logistic regression. We have like our free models are basically in one model has only one digit, the other one has three, and the remaining ones has like all the other ones. And we want to merge them, and of course, do the digit classification task. The figure here shows that. So this triangle is basically because I have like these free weights. So this is alpha 2 and alpha 1, and so the contours, what they show is that if I so if I merge the model with these alpha values, the contour shows like basically for which alpha values I obtain like a certain accuracy on the task. So the 90 there is like all of these alpha values. So if I train my model with from scratch with these alpha values, I will arrive at 90%. And the star is just showing the best one of all of those. And this is the exact solution. So I actually run for each combination of alpha, I run the full objective. And here is, I do model merging through the parameter averaging, and you already can see that this does like a very poor job of first, it doesn't find the actual best combination of alpha, and also it's not very informative because I only can see like around this center, and I have no idea actually how it looks for if I go but a little bit like, see that there is some like, it's kind of skewed towards one of the objectives. So it's actually important to know how these objects interact between each other. And if you go like into the, just.
What exactly are you merging here?
Yeah, so like 3 models. So one model is basically, okay, so I split MNIST into basically digit 1 is only like data 1, and I train a model on that. So it only knows how to classify 1. Another one knows how to classify 2, 3, 4, and then the other one, the rest. So there should be kind of like it's unbalanced. So yes. Okay.
So this is very different from the thing that you talked about earlier, because this is not making the assumption. I mean, here you would not have a common like pre-trained model.
Yeah, this is not a pre-trained.
Okay, yeah, that's true. Yes.
But we also did this on LLM. We have results on LLM, but they
Basically, as long as they are the same model, it kind of works. You have to trust me on that too. So, okay. So, as you can see, if you go Gaussian, then you have like a very idea of how it looks around, and then of course, when you do a mixture with 20 components, of course, you capture more the shape, and then I leave this to Emtiyaz for this one.
Sorry, we're running out of time. So
Yeah,
just take 30 seconds and finish this, and we can take 5-minute break, right? And then we can meet again at 4. But what we showed is that knowledge addition is like multiplying distributions. If you do naive addition in theta space, you get gradient mismatch. And if you reduce the gradient mismatch, it kind of becomes addition in H theta space. So going from a simpler Gaussian to a more complicated Gaussian, you get better approximation. But as Ugo said, you could also add mixture of Gaussian, and you can actually show that this is addition in the pi H theta space using some tricks. It's quite nice. So there you see accuracy improves further. So we're kind of like showing that better posteriors leads to better merging, and it's telling you the difficulty that you shouldn't expect magic by simply adding things. Rather, you should think about estimating the uncertainty or the shape of the objective better by having more information, not just the model parameter. So with that, I will close the talk, and we have 5 minutes. If you have questions, we can answer. And then, maybe we can take the break and then do the questions separately. So we'll meet at 4, maybe? 3. Yeah, 3. Yeah.
We continue at 3 and 5 minutes.
Well, yeah, we could continue talking, and if people want to go for washroom or something, just keep. No, you don't have to. It's not a usual break.
So do you want to ask this question like that or informal chat?
Yeah, no. Let's do the question like this.
No, I think it's very interesting, and so basically when we want to merge models, there's either information loss or not, right? Let's say I go to the easy case. I have an exponential family, okay? I tried with D1 and D2, two data sets. I got theta 1, theta 2. What I should do is I should weight the moment parameters. And then I have no information loss. Right? Because if I have eta 1, eta 2, I take half eta 1 plus half eta 2. The problem is that it doesn't correspond to a linear interpolation of the theta because it's different geodesics, right? So there's some information loss if you try to enforce.
No, I don't think that's true. Maybe, like you're still doing, but you're doing slightly like in each theta space, you do addition, but you can get back to the theta space.
Yes, but when you get back, of course you get back, but you cannot reach that from a linear combination in theta space, because it will be...
Exactly.
And then you have some information loss if you constrain to be on theta, right?
Yeah.
So I think it's very important at the very beginning to know what is the representation.
Exactly.
And here, what you did is you assume that you stay in theta, and then you have to carry some kind of information loss that could be in curvature interpretation with the H matrix.
That's exactly correct.
I think so.
Yes. So things are not linear in the case. Right? In the quadratic case, right? Like they're linear, they're slightly more linear in the quadratic case. And the interesting part is that people ask me, what is the error in posterior approximation? I've actually just shown it to them. Bayesian people should be more excited about it, but it's unfortunate. But you see that the gradient mismatch is exactly the error between a Gaussian with only the mean and the Gaussian with both mean and the covariance. This principle goes everywhere. It's insane.
So basically, if you really want to minimize error, you should allow a fine combination and not convex combination on data, right?
Yeah, it's actually saying that if you only release model parameters, that's not good. You should also release the Hessian of it. It's a very simple thing. So use Ivan or Sophia or whatever, but also release Hessian.
I think that's a reasonable request.
Yeah.
We should make it.
And you'll see that as you want more things, you need to release more. It's just, that's what it is. Yeah.
I had a question on this, because
like if you're not Bayesian when you train the system and you just approximate the Hessian at the end, like how bad is it? Like because
it's not bad. It's okay.
Yeah,
like if you're in
the estimation that you did with Ivan, the other, like have you compared to like a version where you just have something trained normally with HDD and then just estimate the Hessian at the end and then
we do, right?
Yes, it's roughly the same, but the Ivan is not cheap because you don't need to do the extra computation.
So yeah, like you could amortize the cost and just do it when you're training. It's just better to do this. That was very fast. It's already 3. Didn't feel like a 5-minute break. So maybe we continue because I think we took maybe 10-15 minutes more than what we were thinking. So we'll have to cut down in the next part now. So Hart comes to us, but let's go to continual learning part. So now we're gonna try to do the same thing, and in continual learning, now we'll not have like information sitting in space, but it's information coming one after the other. And it's a harder problem because the past can be really big and it grows with time. So we want to connect the inaccuracy of continual learning. And here again, it will come out to be gradient mismatch because what else should it be? Okay. And then we'll try to reconstruct the gradients of the past, and that's where the difficulty lies. And Siddharth will talk about this. So Siddharth, who used to be in Cambridge when he was working with us, and he's in another elite institute in Harvard. And it's based on these 2 works. Sorry. So maybe I could just summarize before I give it to him. So as I said, stability, plasticity, and I think Razwan's going to talk about it tomorrow or some, I think on his talk. But it's also an optimization viewpoint here that gradient mismatch is, now gradient mismatch is between the old gradients and the new gradients that you're computing. And to solve it, I say we must reconstruct the gradients. But this has to be done with finite memory because as time goes by, the past is growing. And what is really amazing is that existing methods, what I see is that all of these methods, they're kind of just ways of reconstructing the gradient and minimizing some kind of gradient mismatch. So you don't like think about, all sorts of different tricks. They're all somehow doing some kind of regularization to make sure that the directions that we take now in our algorithm are similar to what we would have done if we had all the data available at once. Okay, but there is more to it, and that will not be this year, but we'll talk about it next year. But we'll talk about that. Yeah. Okay. So maybe do I need to? Maybe I don't need to show this, so it's fine. So Siddharth, you can. Oh, you have to. Okay.
Okay. So Emti made a bunch of statements, and now I have to show that mathematically, I guess. So the aim is we want to reconstruct gradients of past information. We're going to try and do that using some kind of regularizer, which sort of in this paper we call the knowledge adaptation prior, or it's K of W. So what I've written here is, can you see the mouse? Yes. We want to pick a K of W such that the gradient of that is approximately, or exactly in some cases, equal to the gradient of some model that you've trained in the past. And this model is like, you've trained it on data D old, so this is just sort of classification. I've assumed it's any exponential family loss, but here let's just say classification with a sigmoid model F of W, FW, this is your loss with labels Y and your L2 regularizer. So we want to recreate that gradient. So what we show is this knowledge adaptation prior, the specific form we have does recreate that when you have a lot of past data, and then when you have less past data, you can sort of make some approximations and so on to get to match the gradient as closely as possible, and that shows some insights into how previous methods work and why they work, as well as allows us to improve. Okay, where's my mouse? So the key idea in knowledge adaptation priors is to combine two terms, a function space term and a weight space term, and these are Bregman divergences, so that when you take the gradient of them, things work out quite nicely. This function space term here is sort of between some points, so that you choose some points, input points x, and you calculate the output at those points using weight w, and then using weight W old, and you try and make these similar. And then this weight space term here does something similar, but only in weight space. And the specific form we end up with for this is the following. Sorry, I keep losing the mouse. Okay, so you have a summation over input points. So I've just said M, which is like a subset of your total data set. You can imagine this memory set M as being all of the data or not, which I'll get to on the next slide. But this is just the loss using the soft labels, sigma of F, W old, instead of the hard true labels, YI, over these points, plus a weight space term, which is like the L2 distance between W and W old. I'm going to derive in the next slide exactly why we choose this, but the key point is basically with this exact lost K prior term, the gradients of the K prior is exactly equal to the gradient of the past data when the memory set is equal to all of the past data. So we will get onto the implications of that when the memory set is not equal to all of the past data, but the property that we wanted and we want is that the gradients are the same at all of the past data. So here's the proof. It's sort of, I think, 3 lines in total, of which the first line is a repetition from before. This is just writing out the K prior, but now I've just set M is equal to D old, so this is a sum of all of your past data. You take gradients of this, take the gradient of the first term, well, you have a sum over D old. This is sort of your features, your gradient of the model F. So with generalizing your models, this is like just your features phi I, and sort of this pops up because you have an exponential family loss. This is like your residual, like the distance, the difference between the output with W and W old, and then this is just the derivative of the weight space term. Then we're going to rearrange this, and we're going to add and subtract some true labels. So first term, gonna just put these two FW terms together and subtract yi. Sort of, we're going to add in yi on the right-hand side to make sure everything's fine, and we sort of see that this is exactly equal to the gradient of L old, which is what we were aiming for in the first place. And on the right-hand side, sort of collect together all the remaining terms, and we see that this is equal to the gradient of L old, but at W old. And this is equal to 0 if we have trained W old such that W old is the stationary point of our old loss L old. So we can sort of just cancel that out entirely. And we are left with exactly that the gradient of the K prior is equal to the gradient of old data. Any questions here?
Just wanted to add actually, by the way, the second term is exactly the equation that I use in the monomerging, where it's in a source of the dual, like the condition that Thomas showed. So W old is equal to sum over, W old is equal to the gradient. That's how that red line crossing thing goes to 0. So it's quite beautiful actually. The same, somehow underlines the same calculation, but you don't see it if you're not looking for it.
Okay, so why do we do this? Well, this is nice in a way that we've used W old to make this K prior, and we no longer need the true labels, which is nice, but we do need all of the inputs from D old, which is not so nice. So what happens when we have, so I'll show some results with this, when we just simply use some past data, M, which is like a subset of D old, and we sort of see good results already, and then after the results, we'll sort of try and improve the K prior by reducing the gradient error. So this is just some results on USPS data, sort of binary classification, odd versus even digits. So there's like a very small neural network, just to get an idea of results. Top left is this sort of add new data task, which is like continual learning kind of, but with only one more task. You see the batch performance in gray line is very good because this is a very simple task. K prior in red, as you go to the left of the plot, the memory size reduces, starts at 100% and goes down to 2% of all of your data. So K prior in red remains very good always, whereas a simple baseline here, replay, where you just, over that past data, just add a loss, which is just the replay loss, which is just using true labels over those data points, doesn't do so well. And we sort of show this for a bunch of knowledge adaptation tasks, not just add new data, but also removing old data, which is like unlearning, changing the regularizer, the L2 regularizer term. You can even change the architecture, like knowledge distillation from like a bigger neural network to a smaller neural network, and see similar things always, that the K prior in red is close to batch in gray, unlike the blue replay. And I mean, obviously the paper has a bunch more results and data sets and models. But there is the overall conclusion is always the same. All right, so now we've got something, we've got somewhere to start, we've got some K prior term. But what happens when we have a limited memory M? So for now, we're just going to assume this memory is a subset of D old, and we're going to write out the gradient error exactly, and then we're going to try and reduce this gradient error by changing the K prior or by choosing points cleverly. So what is the gradient error? Well, when M was all of D old, there was no gradient error, which we already showed. So when M is less than D old, then the gradient error is just the prediction disagreement over the points that we didn't keep. And we can make a Taylor series expansion, Taylor series approximation, similarly to how MT did before with the model merging, similar to how we've been talking about so far. And when you write this, well, I sort of wrote it all out. I didn't jump straight and write this was the Hessian, but this term is like the generalized Gauss-Newton matrix here. Except in our case, because we're keeping some memory points, this generalized Gauss-Newton matrix is over d old minus m. It's not over all of the data, it's over the data minus the ones that we are keeping in memory. So we can use this to minimize error in two ways. First, we can choose memory points in M such that this gradient error is smaller. So this gives us ideas on how to choose memory points M. And actually the previous results I showed on the previous slide did something very simple. It just chose points that greedily maximize this second derivative of the lost term inside. This is just like a very simple calculation. It's just sigma times 1 minus sigma. That's one thing we can do. Another thing we can do is to change the form of the k-prior itself by adding in this gradient error to it. And when we do that, it looks a bit like this. So this function space term is the same as before, completely unchanged. This weight space term, if this GW old was 0, if we just ignored it, then this is actually the same as before. It's this L2 difference between W and W old. But now there's an additional GW old Gauss-Newton matrix added in. And that's exactly equal to this term here when we write it up. And this is kind of similar to EWC, right? In fact, when the memory set is empty, is the empty set, then this is exactly EWC. This is the weight prior term that is commonly known in continual learning. Question?
Just only say that generalized Gauss-Newton is the feature, right?
Exactly. Yeah. That's a good point, yes. Generalized Gauss-Newton is the Fisher in this case, and therefore this is exactly EWC or weight priors or whatever you want to call it in continual learning called EWC. Another question? Yeah.
I'm trying to ask why we are using this soft label instead of hard label. Okay, so first, if you have mini memory, I guess in many of the continuing tasks, the label is actually quite small dimension, right? So it shouldn't be too challenging, right? To also, store the round true label for some CLT points. Is that right?
Yes, so it's possible to also use the hard label. A few things. So firstly, the derivation I showed earlier requires using soft labels and not hard labels. And that's what then allows us to write out this gradient error in this way and then get this solution. Secondly, as I will show in the next slide or 2 slides from now, if you use the hard label, that's minimizing gradient error in a slightly different way, actually. So everything I've derived is for generalized linear models. But when you add it, there's an additional gradient error term for if you use neural networks as opposed to generalized linear models. And this additional gradient error term ends up throwing out the hard label from it. And you end up, as we will see in a few slides' time, also having a hard label term, like a replay term.
Yeah, because if you use hard label, right, then this is essentially the core set thing that is done in this Variational continual learning paper, right?
Yeah, but you're saying that's wrong. It doesn't reconstruct the gradient point. It's double counting.
Okay.
Yes.
I just wanted to give another reason to use soft labels. So we found this in RL, that actually using, because in RL you don't actually have targets, you have estimations of the value, and using them just completely doesn't work. Basically, any kind of replay method, it's really hard to do in RL. So the best thing is to try to imitate sort of the outputs of the policy, so trying to imitate a policy rather than rely on previous values. So it's just like a use case where it makes a huge difference.
Yeah, I guess that makes sense. Maybe that's along the lines of, well, when your model doesn't perform very well, like maybe the accuracy is not so good, then using soft labels can be very helpful as opposed to hard labels, right? And this is also similar to just knowledge distillation where soft labels really helps.
So if you want to now optimize this set right of points so that this error is minimized, does that essentially just boil down to the same kind of sensitivity thing, like where you reflect this Hessian term of the gradient thing, or is there some like difference to that?
I didn't understand. But
sorry, yeah, the question was a bit confused. But so if I want to choose now the optimal set of points n, right, that minimizes this gradient error, does that essentially then entail choosing the points with the kind of largest sensitivity, or is that something
Yes,
else?
so you can view it exactly like that. Yes, it is exactly that. So if you want to pick, say, just one point, then you want to pick the one point that is largest sensitivity to changes in like output, basically. If you're picking a set, then you want to pick a set like in an optimal way. The optimal set will be take into account the other points you've chosen and so on, and do that. Yeah.
I think maybe also I want to point out that why we chose to present it in this way. Actually, if you read individual papers, you'll miss this. Maybe in a few years we'll have a unified paper that will say all these things, but we have to do this on case-by-case basis right now. But here you could say, like, if you remove the function space terms completely, then all of the gradients responsibility goes to weight space, right? So then it becomes EWC. So you set the memory. Now we are actually saying that you could trade off the accuracy of your gradients by representing some part of it in the covariance in that Fisher, versus put some of the important things where, let's say you made a lot of mistakes. In this case, the prediction disagreements between the future and the past is very large. The future somehow is very different than the past. So you need to somehow fix those points. And if you store those points like inputs, then you can correct them much better. By just trading off some things. In the paper, if you go and read the weight space, the Fisher assumes something into think the gradient is going to be incorrect on those examples. So you benefit by having this explicit one. Now what Yingjian was saying that using exact labels is also important, and that will come out from here that if the label was wrong from the data, like aleatoric uncertainty, then actually neural networks, that also comes out, and it comes out through the Hessian, which Hossein was going to talk about, and maybe that doesn't make any sense to me right now. But in Gauss-Newton approximation, like Fisher, plus there's a residual times the Hessian of the network. And that residual is the additional error that comes in neural network. So these things are all fitting together and they all go together. So these are three different types of error. It comes from weight uncertainty, data uncertainty, and there is something in between. And you can now choose to pick these three things. Sorry, I spoke the next part already.
That's great, it's easier. I'm actually going to skip the next slide and go straight to that. No, I think the next slide wasn't necessary. We'd already discussed everything already in time anyway. I was going to skip it. So exactly what we were just saying now. You can incorporate the gradient error term from using neural networks as opposed to generalizing your models, and this adds this hard label experience replay term to the loss. And you end up with the improved K-prior, as we called it, which is this experience replay term, which has hard labels, a function space term, which has soft labels, it's like distillation, and a weight space term, which is like the EWC with the Fisher that we showed earlier. And this improved K-prior is like a sum of these three terms, but now is combining these three well-known losses. Like each of these three has been used separately in continual learning, but it's allowing us both to analyze gradient error from each of these terms exactly, as well as therefore providing us ways of telling us how to combine them. For example, the Fisher shouldn't be over all of the past data, it should be over the past data minus the points that you're using in your function space and experience replay terms. And it's also providing us some insights into each of these three terms is a way to reconstruct past gradients, does it approximately in its own different ways, and it's telling us how it does that, which is quite nice. More generally, we can change the weight and function space divergences in the K-prior. So we showed specific, these specific Bregman divergences. And this allows us to recover existing methods. And it's quite something I find very nice. So for example, FROMP, which is this Gaussian process-based approach for continual learning, we can recover that using K-priors and a different function space divergence. And then this gives us ways to perhaps improve upon these methods as well. All right, so my last slide, just some results. This is on ImageNet 1000. So ImageNet 1000 is full ImageNet, but split into 10 tasks. So 100 classes each, 1,000 classes in total. And we're just going to look at test accuracy on the y-axis and memory size on the x-axis. So 0.1% of memory at the left and 7.5% memory on the right of all the past data. We see batch joint, which is trained on all of the data at once, does quite well. Batch separate, which is you train a separate model on each of the 10 tasks and an average performance over all of them. Also does quite well. Online EWC, which is like EWC method, weight prime method, does, I don't know, not great, but not terrible, like 45% or something. We're going to start by looking at vanilla k-priors. So this is just the function space term, like the thing I showed right at the beginning. So just a function space term plus a L2 weight prior term, no Fisher, nothing like that. At small memory sizes, this does quite badly. In fact, EWC does better. But as you increase the memory size, it does well. And then when it gets too large, it starts reducing in performance again. On the left, this is because the memory size is too small and we're not actually using any EWC style term at all, so that's why it does badly. On the right, it does badly because of this. It doesn't have an experience replay term with hard labels, which turns out to be quite important in this case. But the improved k-prior, which has both of these additional terms, sort of fixes this in both regimes. So on the left, we sort of, when you have zero memory, remember, we just recover online EWC. So at small memory sizes, we do very similarly to online EWC. And as we get more and more data, we just continue getting better and sort of keeping the benefits of vanilla k-prior and so on. That's it from me. Back over to Emti. Any questions?
You had a question.
Yes.
I had a question to the last.
Oh, sorry.
It's fine to not pop it up. Is there any way for me to intuitively think about how you're going to recurse on the memory? Because I guess in the beginning maybe you have some megabyte size for 9,000 examples, but then over time you're going to have to replace parts of the memory, right? So when I have random selection, it's trivial. I just throw half of it away at random and populate it with something else.
So yeah, here we didn't look at having a fixed memory size. Here it's growing with task. But yeah, because it's 0.1% of all of the past data, and the past data is increasing over time.
Well, it doesn't matter. Is there still any way to think about it?
Yeah, I think if you go back to this equation, this one, right? We want to pick points to sort of minimize the gradient error, sort of pick the right points in here that do the thing we want. And this is, sure, this might be changing over time, this WO changes over time in continual learning, but this can allow us to help us choose which points are the best to throw away and which points to replace with.
I think this is a very hard question. Yeah. Sorry, maybe I wanted also. This is a very hard question, but this is kind of what the next part we are tackling. And I think all of this comes down to this. So the problem is not solved because your notion of memory changes with time. You can see it here, right? Exactly what Siddharth's saying. Your current parameter decides what that gradient error will be, right? And so in this one, so the next talk is basically telling you there's a better way to think about this than just thinking about individual disagreement and this replay noise that we add. So there's three kind of things, right? Weight term, and then the functional term, but then there's also replay kind of true losses with the true label, right? And you need to think about how to put them together. And the better way to think about this is sensitivity. It doesn't make questions easier, but it at least gives you a way to discretize, form some kind of piecewise linear thing where memory checkpoints can be chosen, yeah. Just
a quick yes and no follow-up. So that means you're also literally just storing the data examples. You're not actually also storing some sort of sensitivity-related value.
No. We're storing.
It's not like a weighted course.
Yeah. So
weight, right?
This was done before, right? So now we have developed the theory on sensitivity, we are still thinking about how to do this. So that will be a great thing to work with people. But yeah, we don't know exactly how to, but we think something, a representation of input space, like pseudo images, pseudo inputs, plus some actual data, plus some model. So we think it's a combination of these three. Yeah. Yes or no? Yes. Okay, maybe that's what I was saying. Maybe.
Any other questions?
You're right on time. Great. Yeah, I'm sorry I'm being annoying, but you know, this is Crest Day. This is what it means actually. Yeah, just giving this thing. So Siddharth talked about this, right? And I just want you to think about this picture that I think was shown in the previous last week, right? And we think about this, and many people say continual learning methods can be put into these labels, these categories, but actually I'm saying this is really wrong. So that's what I wanted to do, is feel satisfying. I love saying wrong, right? But I think this is really harmful if you think like this, because it looks like that there are many, so there's regularization based method, it fits somewhere in between. But I'm trying to say that it's all regularization, right? It's somehow regularizing the gradients, somehow regularizing the representation of the problem. And you need to make sure that the new model is somehow close to the old model in some way, right? And so we're trying to bring a little bit principle here. Sorry, I shouldn't have been that harsh, that it's completely wrong, but we need to rethink these things, and perhaps we can, you know, bring more principles back into this field. That's kind of, you know, there's so many continual learning papers these days. I'm just very scared to get into this field. Okay, so this was the summary just to give you. It was about gradient mismatch. All existing methods can be seen as different ways to reconstruct cross gradients. But there's a little bit of more things, like what kind of mistakes are being made when you make these finite memory choices, and they can be actually written quite precisely. And I think this could change the way we do this this field, but wait for that next year. If we are successful, we'll present it next year. Okay, so let's go to the next part, which really is kind of, so first we talked about model merging, right? There, all the data was present in both models, so we didn't have to think about memory. But when we come to continual learning, we realize that when we need to make sure that the future and present, they agree, the gradients are matched, then you need to represent the past, because the past is very, very long. So you somehow need to make sure where to make sure that the gradients match. And that's a hard question, you know. Just look back in my life and think about those things that are memorable, that I remember, that made me who I am. And I use those moments, what I learned, moments or maybe periods of my life, the knowledge that I gained, that I use in the future. So the kind of where we are going, you can see why this topic is important. So memory, actually, probably we spend most time on this. And so we have one paper on it. We spent 4 years on it. We have one paper on it. I'm very proud of it, that we didn't write 15 papers. So I think it's a good paper. And it's like K-priors also, I'm very proud of, because it's a good paper that I learned a lot from that. So this is that kind of work. And Peter and Lou, they both kind of graduated and left. But Dharmesh is still here, so he's going to talk about some parts of this. But I'll give a little bit of prelude, as I did. So we have about exactly 30 minutes. I think that'll be enough, right, for us to do. Okay, so let's think about this. So I took ImageNet. I have gone to ImageNet, and I picked one class, and I'm showing you some examples from that class. Which class do you think it is? If you've gone to Dharmesh's poster, then don't answer. Which class is this? Can anybody say? Make a guess? Ice cream. Wow. that was a good guess. Yeah. I don't know, what is it? Trains? People? Okay, so it's hard to tell, right? These things somehow are not really representative of what the class is perhaps. And how about this class? What is this? Traffic light, yes. Okay, let me see. Oh, traffic light. Actually, it turns out both of them are traffic lights, okay? So the top one and the bottom one, they're both samples of traffic lights. But what I did actually, I have computed somehow sensitivity of the model to this data examples, and the high sensitivity ones are at the top and low sensitivity ones are at the bottom. Meaning that if I remove these examples from the training data and I retrain the model doesn't change much. That's the bottom one. Okay, you can see that there are lots of examples like this. These are like regular things that are abundant. And the top one are the rare things that lie at some kind of far distance. Maybe they help us to understand how traffic light is different from trains, right? How they're different from people or cars, I don't know what this is, or sky, right? So these are somehow lying and they're telling us how this class differs from other classes, okay? So if I ask you a question, which points here are memorable in the classification setting, you'd have to think about it a little bit harder, but you'll come up with the answer that we think is correct, right? So somehow you need to discriminate traffic light from other things, and some examples are really lying in that boundary with some other class somehow, or maybe they're on the wrong side of the boundary and they are highly okay. You could do this again actually, so like it's the same, you know that this is not the class that you see. So would you want to take a guess on this? Come on, it's very good. So, huh? Ah, come on, Julian. I think Julian is a dog, he likes dogs, so you're actually right. It is Chihuahua. But you could say that low sensitivity images, right, they're at the bottom, and they really have got Chihuahua, right? But the top ones are somehow crossing boundaries with other dogs, or maybe people with dogs, right? And they would be somehow in the boundary with them, right? So they are telling us what the boundary of our knowledge. I love this word, and I learned this in 2019 in somebody's news tutorial actually. So we're trying to figure out boundary of knowledge. And the way to figure out boundary of knowledge is to understand how that boundary can be changed, right? And that boundary can be changed by understanding the influence of the data example on the model, right? How much this example influences the boundary. So there's already a known concept on this, which is called influence function. And the way that it actually works is that you look at your old model, right? And you think about what happens if I take this data examples and take this far from the data example, right? Then the model changes quite a lot. And this model is a little bit, sorry, the data is a little bit far from the other data, then the model changes quite a lot. Right? So if the model, maybe I'm having difficulty predicting, or if the model is somehow uncertain, it should have a larger effect in the change. And that effect is kind of written in this way. You could see that it has Hessian in the gradient, so somehow you could think that it will be somehow related to some kind of posteriors, which is where we are getting to, okay? Now the issue with this influence function that everybody is complaining about and then saying, when I start work on this and talk to people, they all say, and I think Yingjian also said that today, that these are all per data example, you know? These are per data example things, so they're not used for groups somehow. This is a misconception. It's not true. But somehow people don't use it like that because they cannot see it. It's just hard to see it in the way that it's written. So it's not used for group removal. It's only defined at the convergence, like theta star has to be at optimum, and then you work backward, you do a Taylor series expansion and think about perturbation at that local minima. That's how you come up with this, second order effect, right? So that's the difficulty that you say, oh, I need to invert a Hessian. If I don't invert a Hessian, I cannot do this. Well, I think you kind of didn't think this through. You just have to think about it right perturbation. It doesn't have to be that hard. okay? So we now say, let's actually try to do this from, the way that we know it, all the way that we know it. This is where we start, okay? So what I say is that if influence function is correct, under those settings, I should be able to rederive it from this equation. So that's what we did. Okay, you start with the Gaussian, and you can guess the answers, the mean and the covariance, both because mean will bring the theta, and the covariance will bring the Hessian. And then you try to do subtraction here. So you just plug this in a least squares model and do subtraction, you will get that equation out of it. Okay, so that's what is written in that paper. And hopefully Dharmesh will actually say a little bit about this. But what essentially we're coming to is that we can actually now, because this equation is more general, it doesn't require optimality, it holds at every iteration. Now we can do this at every iteration, even when you have not conversed. And because this dual representation is additive in natural parameters, we can also do group level removal, because we can simply subtract many things at once, right? There's no doubt here. You can just add many things or subtract many things. So you could do group level things. And you don't need to be at the optimum. You could do it at every iteration. And what was the third thing? You don't need to invert the Hessian, because we're going to just do something like atom or gradient descent. And if we do gradient descent, we'll only use gradients. If we'll do atom, then we'll use the variance and the gradient. That's what it will come down to be. Okay, so we're not inventing influence functions, we're generalizing them. So I call it influence measures. So when I say influence measures, stop thinking about Hessian inversion, stop thinking about one data example, stop thinking about optimality. This is strictly more general. It frees you from all those preconceptions that you have if you just think about influence functions, okay? So I hope that you will have this kind of picture in your mind rather than what people have been talking about in influence function literature, is that you start learning something, you have iterations, right? You're training and you're not finished. You're still training and you're somewhere in between, but you want to understand somehow what would happen if you did something else in your trajectory. Now, if you truly want to do this, you have to retrain. Right? If you remove some example, let's say here, the trajectory becomes different, you have to retrain it, but that would be very hard. So let's try to think about a first order estimate from here. So again, I'm not claiming that you could do this exactly. It's just a first order estimate, but done kind of right, so you don't have to wait for optimality. You don't have to wait until completion or until your GPT is trained and then do on it. You can actually do it anytime. Okay, so we're going to estimate this. And essentially what you will see that comes down to simply taking one natural gradient step backwards, meaning running your atom optimizer one step backward. It's just taking one step back, okay? And then that gives me a generalization where instead of using Hessian, I plug in the variances. It's the inverse of a Hessian, I just plug in the variance, okay? And there are other versions where I can use the mean, or I can sample from my model and then compute this. But all of these computation is very, very simple because I just compute prediction variance and prediction error. So we're not going to prove this, but if you actually, Dharmesh will show this in his slide, how this comes out to be. But that's basically what we'll do. So Dharmesh, do like 10 minutes?
So your slide?
Yeah.
Let's keep this one.
Yeah, you can use a mouse like this.
Okay, yeah, sure, sounds good. Okay, so I think back to MT's kind of brain in the cog picture. So we have the posterior here, which is made up of parts. We have the prior, we have likelihood terms for each example, and any one of these parts can be perturbed. So perturbation basically here means we can replace that part, we can delete that part, we can reweight that part. So there's all kinds of perturbation functions. And this perturbation function is basically enacted on the posterior, and we measure the change in the model, so the sensitivity of the model to perturbation. Sensitivity, again, can be measured in different ways. From Bayesian perspective, that could be some kind of posterior quantity, but really can be anything like what you really care about, and this work here is motivated by looking at data influence. So that's kind of looking at what is the sensitivity to perturbation in the data. And so in red, you can see here that the perturbation function corresponds to basically dividing through the posterior by a likelihood or a group of likelihoods. So this math cal m here corresponds to the examples that you want to perturb. And we simply divide through the posterior by those to get, in this case, say for the left-hand equation here is showing the general thing. So it's obviously as hard as doing the Bayesian inference problem itself. But thankfully, it turns out that in conjugate Bayes, things are very simple. Unsurprisingly, it corresponds to very simple computations. And those computations, so on the right here, I've written just what's on the left here in exponential family form. And you see that to get this perturbed posterior, it's simply subtracting from the actual posterior natural parameters. We subtract from that these local likelihood parameters. So again, we call this like lambda tilde, and that'll become more clear when I sort of draw this connection to the more interesting complex cases that show in the next slide. But keep in mind this blue box here. This is quite a fundamental, but quite important equation to keep in mind, that this deviation from the perturbed posterior from the actual posterior, it's simply given by just adding up these local likelihood parameters. Okay. So when it comes to kind of more interesting cases, how can we extend this principle? And so if you recall, like the Bayesian learning rule can be actually viewed as at every step doing this kind of conjugate Bayes sort of inference. And I should probably, I could flick back to, I think Emti had this equation. I don't think it's not too far away. I can maybe go back to it. Maybe this was a bad idea, but it's, this one, I guess. So you can see here that this is the VLR step, which essentially what it comes down to is that the local natural gradients, they are like these local likelihood parameters. And so that comes into this deviation here. So of course, this is not the exact deviation. There's a hat on lambda t minus m, but it's given some sense of what the effect on the model would be if I were to perturb by removing examples in m. And the key principle is that large natural gradients imply higher sensitivity. And what we observe in practice is that just a few examples often account for most of the sensitivity. And we call those examples the memory of the model. And I show one example of this here at the bottom. This is a ResNet 50 train on ImageNet using IVON. And you can see that there's a kind of heavy tail distribution on the sensitivities, on the influence. Some call this long tail. Note that the y-axis here is log scale, so it will look even more kind of heavy-tailed if you were to plot this in the usual fashion. As you keep training, or you sort of go from a less to a more complex model, then this tail gets longer. The model is more sensitive to a few of these examples. This is just repeating kind of what Emti just showed actually before. So for 3 of the classes in the ImageNet datasets, what are some of these kind of low and high sensitivity cases? And in general, we observe that kind of low sensitivity examples are kind of prototypical examples. There's like not much diversity in the images. Like it's the main object of the label appears quite prominently in the frame, whereas these high sensitivity ones are obviously much more unusual. They're kind of atypical, non-prototypical examples. In many cases contain like noisy labels, like in ImageNet, if you worked with this data set here, it has many problems. It was obviously crowdsourced, that's what we usually do, and so it's not perfect. And actually you can detect many of these mistakes in ImageNet. So I think from this kind of general memory perturbation equation, how can we kind of derive the sensitivity measures, the influence measures for different algorithms? Well, it's quite a simple story, right? From the BLR, you can make certain choices, approximations to obtain, say, these algorithms from the the Bayesian learning rule. In the same fashion, you apply those same choices to derive the sensitivity measures for different algorithms. And in the first row here, you see Newton's methods, which essentially recovers the influence function that is quite commonly used, proposed for deep learning by Cohen and Yang. But the really cool thing is that we see automatically that the measure is already valid at every iteration. There's no need for, they derive these things by basically looking at the stationarity condition, they derive this like linear response curve, so it depends upon the automatic condition. Here, automatically, it comes out to be a sensitivity measure at every step. But we can go beyond this to adaptive gradient-based methods, like ADAM and RMS prop, where the computation is very simple. It's just exploiting, reusing information that one already has during training. And that's using the scale vector, basically, that just multiplies element-wise the gradient. And people have kind of motivated in previous works some measures for, say, gradient-based methods, SGD, for instance, for tracing by Google, have this paper. So we also get something like that as well, following through with this view on choices and approximations that you make. So yes, how do we get this kind of perspective of sensitivity being this kind of combination of kind of the variance and the error? Well, okay, so let's look at the change in model output, say logits for classification. In the first line, we take a Taylor expansion of first order, and then we plug in to the theta minus I minus theta, this part over here. We plug in the Memory-Perturbation equation. I mean, actually, in this case here, it's just the influence function, the first row in the table that I had. And if you just write that out, then you see that you get these two parts, where the first part in blue looks like is the prediction variance, and the second part is just the residual, essentially. And this may look like a very particular case, like I've picked, the deviation in the sort of the outputs, but if you've actually looked at some of these, very classical papers like Cook and others in the 70s and 80s, they really show that it doesn't really matter what kind of measure you use. Like it could be in the outputs, the loss, whatever. The KL between the posterior and the perturbed posterior, it just comes down to being a combination of these two fundamental quantities. I've got a post about that as well, which you can come by and check out if you're interested in that perspective too. And this can also be extended to other kinds to groups of examples as well in a very similar way. Yeah, so here, so back to kind of what we saw in model merging, we can look at the effect of what would happen basically if we kind of perform, say, like removal of a whole class. So we kind of estimate the effect of removing kind of all the examples they belong into a given kind of MNIST class, and yeah, we're comparing that to what would be the actual effect from brute force retraining, and there's very good alignment of these two things. So it's showing that actually like this local perturbation kind of quite accurately reflects what would happen to the actual system if we retrain. And yeah, so we have this way of estimating the effect of dropping out an example, and so naturally that can be used to get a kind of estimate or to approximate the leave one out objective, which is obviously quite popular in cross-validation. It's obviously a proxy for optimization, and so what's really cool is that we can actually get this approximation during training. Like I think most previous works have only been doing this at the end of training, but this also works during training as well. And we compare, that's in the black line here, and that's compared against the test error, and we show many examples of this, and there's very good alignment between the two. And what we also find is that we try this for different settings. So we try this for kind of ADAM during training. We try this for like doing some kind of like sort of GGN staffing, that's approximation during training. We try this for IVON, and we find that more faithful kind of reconstructions of the variance actually give a better match to the test performance. So pass on.
There are questions for Dharmesh? We have 8 minutes left, so we are good. All right. I'm sorry, Dharmesh, but I'm going to go back to my favorite slide. This, he was humble and just glided over. So let me come back. This is really amazing, actually. This is kind of what convinced me to actually, submit the paper. Otherwise, I was not very sure if this was good enough. But when I said in the beginning, I started with the trustworthy system, right? What we really need, if you're able to make a trustworthy system, you need to be able to answer what-if questions during training. So when you're actually putting in data into your training large language model, right? At that time, you want to be able to think about what would happen in the future. What would be the effect of this addition? Now, this is doing backwards. This is saying, what would have happened if I removed the MNIST? But it's kind of the same question, right? And here, this one is obtained using this very simple first order estimate. So this y-axis is through what Dharmesh presented. So it's, if you actually just took one step backward of your optimizer with this class. So this is not one example, please, huh? This is whole class. So each marker here, so this is like, I'm removing class 9 from LaNet training, okay? And you see the natural gradients are actually additive in this. And it's not like it's too hard to compute this quantity. I mean, you have to actually make slight approximation if you want to make it equivalent to just doing one gradient step, but it's doable. You don't have to retrain the whole thing, okay? And this simple one step backward of your algorithm is just this, right? And this matches quite well with full retraining. And you can see that if you did this for class 3, class 5, class 2, they are all estimated quite faithfully. Actually, if you throw in a little bit more effort, you can make this almost exact. And at the time when we wrote the paper, we didn't do it because we didn't understand it at the time. But I'm just kind of trying to say that these first order effects, when done right, they can actually really estimate things without having to retrain stuff, right? And we're trying to now develop new stuff to say, like, can we take a few steps of training? So let's say if I took 5 steps and I should get really as large decrease as I want, can I do that? And I also showed you in the beginning that model merging also is related to this kind of sensitivity. So you could think about, like, can I just fine tune on something for 10 steps and subtract that from my model to know what would happen, right? But we're beginning to go towards this trustworthiness thing, understanding the reliability of our components because we are asking these what-if questions. And we need more of these techniques to do it. And this, what we do with Bayes-Duality is just kind of one set of ideas to do this. But I hope that this would be the takeaway, that actually we don't have to just, rely on these LLMs. Your boss is telling you to all work on LLMs. You don't have to do this, We can actually, really, I heard that even more now. I'm kind of terrified, right? We can actually make systems that are not trained in the way that people are training them. We can change how we train our AI systems fundamentally. We can bring in more transparency by thinking about what data examples have affected our decisions in the future. What training choices that we made that actually are crucial, such that if we didn't make those choices, the model would be completely different. Then I need to log this, I need to report this. It needs to be open sourced. And if you can't release that data, then don't use it, right? So we have to do this sensitivity analysis, and I was calling stress testing before, but I would like to push our community towards that side. And so let's think about it, and I know many of you also share this enthusiasm with me, so thanks a lot for listening, and maybe I'll just end with showing you, right? So this is what I was talking about, reliable building blocks, and I kind of showed that somehow, because this natural gradient thing is additive, it is helping me to understand what the importance with each block was, What could happen if I removed it, at least locally? We need to work more on this to do more global effect. Maybe that will require retraining a little bit, but we need to figure that out. So this is a thing, and thanks a lot for coming here and listening to us, and happy to talk about this for the rest of the workshop. Thank you.
I think we have a few minutes left for questions. So.
Thanks. If you can go back to your favorite slide. So I was
it's on
just wondering
MNIST,
why these like MLP and Linux lie on different lines. Like, is it that the kind of y-axis is essentially arbitrary units, or like, so why don't they all lie on the diagonal essentially of this plot?
Yeah, they are arbitrary units, right? The number of data examples is different, the number of parameters are different, so they make sense within. So like it's sum of few things, right? And in LUNET, in LUNET, this sum is different than in MLP, right?
Okay, so is there like a way to convert this? Like, I mean, if I get this estimate from the y-axis with your method, right? Like, can I essentially like figure out the NLL directly, or do I have to try this what you did here and then like?
You mean if you want to compare models, how do you do it? Is that what the question is?
Yeah, I guess I can. Essentially, my question is like, if I ask you what's actually like the NLL, like that's what I want to know, right? But I don't want you to run the experiment on the x-axis. I just do the estimator from your y-axis. Like, can you directly, for any model I give you, compute this, or do you have to empirically fit these?
No. You can just do it for any model.
Okay,
Yeah.
so this is all like, so you can predict these slopes, like these are not just like fits
Yeah.
to the data.
Yeah. I mean, if I made this plot, I'll make it differently, but postdocs made it, and I don't have access to it, otherwise I won't show it like this. To start to
I have been very excited about data removal, okay?
Excited, okay. Data removal, thank you.
Yeah, data removal, okay, or data deletion as a way to actually do model editing. I actually checked about these things with my colleagues doing security. They have a slightly different opinion. Maybe I want to hear your opinion. So first thing about validating or verifying data deletion or data removal, you need to do something that they usually do, like membership inference attack. Right? But then the question they raise, or as I understand from my colleagues, is if you can actually do this kind of membership inference attack to verify you have successfully deleted the data, then in some sense you are violating differential privacy in the sense that, okay, if you can verify that this has been deleted, then more or less you know that, okay, I can check, what other details I have checked, right? So what's your opinion on that? So this privacy thing is also like an important component for ASAP, I guess.
Yeah, I completely agree with this, right? So I think it's not on me, right? People who are selling unlearning as a way to avoid lawsuits, I think they need to rethink these things, right? You also want security, but you also don't want to tell what you're putting in your model, and you don't want to pay for it or check whether you're putting the right things in. You can't have it all, right? So I completely agree with this. Like, I think that these things are conflicting, right? You want to unlearn things, but you also want it to be private. You have to make this decision when you design the model. If you cannot release this document, this data examples to public, you should not put it in there, right? Because it's somewhere in there in the model. Or if you put it there, then you have to put so much effort that you don't have to unlearn it later on, right? So you don't put in garbage, please, in my food. Like, who wants that, right? Maybe I'm pissing off a lot of people, but that's kind of the point of this conference, this workshop.
So unlearning is not just for the kind of use cases that you described, right? Like, it might be the case that you start training a model with some data, like you had permissions to do it, but then like you have to remove it because the person who gave the permission is revoking permission.
Yeah, then restart. So you're right. I think this is not easy, right? Like you don't you start building a bridge and you say, oh, well, I made a mistake somewhere. It was somebody else's land. Oh, did that happen somewhere? And then, so you have to break the bridge, right? You don't say like, oh, let me give you a casino or something.
Maybe I misunderstood something you said, but is the idea that the sensitivity that you're computing here, like somehow, like basically you say, I want to have this information at training time and then use it to make decisions of whether I'm going to influence some data or not. But like if I'm thinking, say, from a privacy point of view, the fact that the model is not necessarily sensitive to this data point, it doesn't mean that I cannot reconstruct that information from the trained model. So it just feels like there's still sort of some disconnect where sure you have this sensitivity, this doesn't tell you if the data is harmful or not. And if you just use this to like filter to see how many data points the model is sensitive from like a trillion size data set, you probably get a few billions, which you can't inspect anyway, so you can't say anything about it. And it doesn't necessarily help you on the privacy front because just the fact that at that point in time, that data point doesn't seem to contribute much to the loss, doesn't mean that that information is not somehow in the model.
Yeah, I hear you. We're 3 minutes over, so I apologize because we've been trying to be very on time, but let me, I completely agree with you. I think we need to do more work in like trying to understand what we want our models to do. Like, so when we design vaccines, we say we have control groups, people with heart disease, people with this kind of, all sorts of side effects. We think about this, and that's our test kind of set, right? So when we are actually training things, we need to have all of these issues, not just accuracy in mind, right? And so your system would be as good as your stress test is, right? So if you have, of course, unknowns are hard, but you have to think a lot before you start to train, on some filthy data, some large model, and sell it to people. So that's kind of what I'm saying. Because you're right that these trade-offs they don't just go away. And that's why we pay money to people who provide a service, right? That's their job. Yeah. Sorry, so maybe we should close the meeting with that, yeah.
Yeah, so maybe let's thank all the speakers again.